Hello, my dear Neet and JE aspirants. This is very high voltage P block session. Many students worried about P block. Sir, how to study this P block and how to remember these P block concepts and how to apply these concepts even after studying many times. So I'm going to forget this P block concept. I'm unable to apply these concepts. So for all these questions, for all these problems, one solution is studying P block simultaneously. So don't study P block 13 group separately, 14 group separate, 15 group separate, like that. Don't study P block. So if you study all properties of 13 to 18 groups simultaneously, it is very easy. It is very easy to remember and very easy to answer those questions. For example, occurrence of 13 to 18 group elements simultaneously and physical properties of all 13 to 18 groups simultaneously, if you study, easily you will remember, easily you will understand those concepts, right? Anomalous properties. So boron anomalous properties, next carbon anomalous properties, oxygen anomalous properties, nitrogen anomalous properties, like this. Anomalous properties of all elements from 13 to 18 group, if you study, it is very easy to remember and very easy to understand and very easy to apply those concepts in the exam. So here in this session, I made all these properties from 13 to 18 groups simultaneously. I hope you will get benefited with this session. So let us start P block revision. P block elements are from 13th group to 18th group elements. These 13th group elements are called boron family, 14th group elements carbon family, 15th group elements nicogens. These elements are called nicogens because nicogens means poisonous gas producers. Among all 15th group elements, all hydrides except nitrogen, all hydrides except ammonia, other hydrides, phosphine, arsine, stevine, bismuthine, these are poisonous gases. So due to the formation of poisonous gases by 15th group elements, these elements considered as nicogens. 16th group elements are halogens. 16th group elements are chalcogens. Chalcogens means mineral gas producers. Almost all minerals are coming from oxygen and sulfur. There are very few elements like NaCl. There are very few minerals like NaCl and KCl. NaCl is a rock salt, right? KCl is sylvine. So, like NaCl and KCl, there are very few minerals are possible without oxygen and sulfur. Almost all minerals are coming with oxygen and sulfur. So that's why these 16 group elements are called as chalcogens because they are with oxygen and sulfur. Next, 17th group elements are halogens. Halogens are salt producers. Most of the salts are coming with halogens: fluorine, chlorine, bromine, iodine. And these salts, maximum percentage of salts available in the seawater. Next, 18th group elements, aerogens, noble gases. So aerogens means they are available in the air, they are abundant in the air. Around 1% of the atmosphere, noble gases. 78% nitrogen by volume, 21% oxygen by volume, around 1% noble gases and other gases. So major composition in that 1% is noble gases. Right. Now here one important point we need to discuss. What is that? In boron family, last element, carbon family, last element, 15th group, last element, 16th, 17th and 18th group, last elements are artificial radioactive elements. Man-made elements are artificial radioactive elements. And how do you get artificial radioactive elements? What is artificial radioactivity? What is artificial disintegration? So artificial disintegration means that particular element nucleus is stable. It won't disintegrate by itself. But when this nucleus is bombarded with any fast moving particle, it undergoes disintegration. Its nucleus is going to blast and produces smaller particles or other particles and radiation. This is artificial disintegration. So all man-made elements are coming from artificial disintegration. What is natural disintegration? Its nucleus is very heavy and it is unstable and decomposes to produce relatively smaller particles and radiation like alpha decay, beta decay, like that. So From 13th group to 18th group, the last elements are artificial elements. They are coming from artificial disintegration or artificial decay. Right. I will give you a clear example for this natural decay and artificial decay. What is that? Radon is one of the noble gas element. It is coming from radium with natural disintegration. And oxidation is the last element of noble gases. It is coming from artificial disintegration of californium with calcium. When californium is bombarded with calcium, it is producing oxidation and neutron particles along with some radiation. This is artificial decay. So here the important point is oxidation is coming from artificial disintegration of californium and calcium, and radon is coming from natural disintegration of radium. Next, all these last elements, radioactive elements, what we discussed, their half-lives are very less, within seconds or fraction of seconds. And this was very clearly mentioned in the NCERT. There is importance for this half-life. What is the importance? The elements whose half-lives are very, very, very less, minutes, seconds, or fraction of seconds, their activity is very high. Their radioactivity is very high. They emit large amount of radiation. But the elements whose half-life is very high, their activity is less. I mean, their radioactivity is very less, and they are harmless. They don't cause any harm. For example, carbon-14. Carbon-14 is a radioactive element. It emits radiation, but its half-life is what? 5,770 years. It's a very long half-life. It will take very long time for disintegration. So it emits very less radiation. So it does not cause any harm to us. So here the point is, the elements whose half-life is less, their radioactivity is more, and their harm is more. They are dangerous. The elements whose half-life is very high, their radioactivity is less, and they are less harmful. Right. Next, coming to next topic is occurrence. So here I have given all the sources or minerals given in the NCERT, only NCERT sources. Especially in organic chemistry, you should study only NCERT. No need to study anything beyond NCERT. No need to go for reference books. So no need to go for any Google examples. Just what is given in the NCERT, you read. That is enough. If they want to ask any questions regarding occurrence or physical properties or chemical properties, whatever it is, within NCERT and NCERT application only. No need to go beyond NCERT. Right. So let us see what sources are given for different groups in the NCERT. 13th group, orthoboric acid, borax, kernite, bauxite. 14th group, in elemental state, for carbon, in elemental state, coal, graphite, diamond. In combined state, carbonates, hydroxides, and carbon dioxide. Next, silicon occurrence. Silicon sources are silica, silicates, ceramics, glass, and cement. And tin, cassiterite, SNO2, galena, PBS. 15th group occurrence, nitrogen. Nitrogen is coming from the nitrates. Chili saltpeter, sodium nitrate. Indian saltpeter, potassium nitrate. And phosphorus is coming from apatite family. Apatite family is Ca3PO4 twice and CaX2. Where X is, it can be chlorine or fluorine or OH. If fluorine is there, that is fluoroapatite. If chlorine is there, chloropatite. If OH is there, hydroxyapatite. Right. Now, 16th group occurrence, 16th group examples, minerals given in the NCERT. Sulfur, gypsum, CaSO4, 2H2O. Epsom salt, MgSO4, 7H2O. Baryta, BaSO4. Galena, PBS. Zinc blende, ZNS. And copper pyrite, CuFeS2. 17th group, fluorspar, CaF2. Cryolite, Na3L, AlF6. Fluorapatite, Ca3PO4 twice, CaF2. Rock salt, NaCl. And cornellite. Cornellite is a double salt which is KCl, MgCl2, 6H2. 18th group elements except oxygen and radon, all noble gases are coming from the atmosphere. Around 1% composition of the atmosphere by volume is noble gases. Oxygen and radon are coming from radioactivity. Already we discussed. Radon is coming from natural disintegration. Oxygen is coming from artificial disintegration. So this is the occurrence. Now some important points related to their occurrence and nature. Aluminum is the most abundant metal in the earth crust. If the question is, what is the first most abundant element? Aluminum. If the question is, what is the most abundant element? Most abundant metal is aluminum. Most abundant element is oxygen. Second most abundant element is silicon. And third most abundant element is aluminum. First most abundant metal is aluminum. Next, ultra pure silicon and germanium are used as semiconductors and transistors. So why only the silicon and germanium are used as semiconductors and transistors? Why not other elements? There are two important reasons. One reason is the silicon and germanium. We can use these two elements to get the precise electrical conductivity. Not very high, not very less. I want a particular range of electrical conductivity. Then we can use silicon and germanium to make it by doping. Addition of impurities is doping, you know that. So to get precise electrical conductivity, the silicon and germanium are more useful. And second point is they are most abundant. Their percentage in the earth crust is more. So because of these two reasons, silicon and germanium are used as semiconductors. They are used in transistors, right, in pure form. Next, another important point is seawater contains chlorides, bromides, hydrides of sodium, magnesium, calcium, and potassium. Next, coming to physical state, appearance, atomicity, and isotopes. First, 13th group. 13th group, first element is boron. Boron is very hard solid, very hard black solid. What is the reason for its hardness? So boron has icosahedral structure, B12 structure. It has B12 units. Means 12 boron atoms are bonded with strong covalent bonds. So because of this network covalent bonds, it is very hard in nature. And because of its network crystalline structure, its melting point is very high. Among all boron family elements, highest boiling point is 2453 kelvins. Next, gallium. Gallium has two interesting points. Gallium is called as summer liquid and it is used in high temperature thermometers. So why it is called summer liquid means gallium melting point is 30 degrees Celsius. 30 degrees Celsius means just above the room temperature. Generally in summer, temperature is always more than 30 degrees Celsius. So it exists in liquid state always in summer. So that's why it is called summer liquid. The second point is gallium melting point is 30 degrees Celsius and boiling point is 2400 degrees Celsius. Means from 30 degrees Celsius to 2400 degrees Celsius, gallium is in liquid state. It has the vast liquid range. This property is used as thermometer. Gallium thermometers. Gallium thermometers are used to measure high temperatures. Sir, why not we use mercury thermometer? Why can't we use mercury thermometer? So if you try to find the higher temperatures by using mercury thermometer, at high temperature, mercury is going to vaporize. But gallium does not vaporize. Gallium up to 2400 degrees centigrade, up to 2400 degrees Celsius, it won't vaporize. It will be in the liquid state. So one point is what? Gallium is summer liquid. Another point is what? It is used in high temperature thermometers. Next, aluminum is bright silvery white metal and it has high tensile strength. It has high thermal and electrical conductivity. Here the most important point from the NCERT is the most or the highest electrical conductivity is for silver. The second highest electrical conductivity is aluminum. And third highest electrical conductivity is for copper. Aluminum electrical conductivity is greater than copper. And in NCERT, it was clearly mentioned that the electrical conductivity of aluminum is double the copper. This is the important point here. Next, boron has two isotopes, boron 10 and boron 11. The atomic mass of boron is around 10.8, approximately equal to 11. So whenever an element has two or more isotopes, its atomic mass is not the atomic mass of any isotope. We have to take average atomic mass. So how to take average atomic mass? So here you have a formula, m1x1 plus m2x2 plus x1 plus x2. m1 and m2 are atomic masses of the given isotopes. x1 and x2 are their percentage abundance or ratio or mole fraction. If you substitute this boron data in this formula, you will get 10 into 19 plus 11 into 81 divided by 19 plus 81. This value you will get 10.8, which is approximately equal to 11. So boron atomic mass is 11. Next, 14th group, carbon black, coke, charcoal are impure forms of graphite and fullerenes. Fullerenes are the most pure form of carbon allotropes. Among all amorphous and crystalline allotropic forms, fullerenes are the most pure form due to absence of dangling bonds. What are dangling bonds and why these fullerenes do not have dangling bonds? We will discuss in the allotropes. Carbon black is obtained by burning hydrocarbons with limited supply of air, and charcoal is obtained by heating coal and wood in the absence of air. Carbon has three isotopes. We know that carbon 12, carbon 13, carbon 14. Carbon 12 and carbon 13 are non-radioactive isotopes. Carbon 14 is radioactive isotopes. Next, coming to 15th group elements. In 15th group elements, nitrogen is diatomic. In 15th group elements, nitrogen is diatomic. N2 is diatomic. And phosphorus is tetraatomic. Why nitrogen is diatomic? Why phosphorus is tetraatomic? Similar reason is coming with 16th group elements also. Oxygen is diatomic O2, but sulfur is octoatomic S8. Same reason for this O2 and S8 also. Now let us discuss why nitrogen is exists in a diatomic state and phosphorus is existing in tetraatomic state. Take nitrogen, outer configuration 2s2, 2p3. So in 2p, 3 unpaired electrons are there. 2s is completely filled. P has a 3 unpaired. According to VBT, only the unpaired orbitals can participate in overlapping. So this is the first nitrogen p orbital. This is px, py, tz. Second nitrogen px orbital, py orbital, pz orbital. Here we have one important fundamental point. That's why we are discussing this. Assume x-axis as internuclear axis. X is our internuclear axis. So X is internuclear axis means px gives sigma bond and py involves in sidewise overlapping gives pi bond. pz involves in sidewise overlapping gives pi bond. So here first nitrogen px, second nitrogen px involves in direct overlapping and gives sigma bond. And suppose these two are py orbitals involves in sidewise overlapping gives pi bond, and this is pz orbital involves in sidewise overlapping p bond. So in between two nitrogen atoms, 1 sigma and 2 pi bonds are formed. 1 sigma and 2 pi bonds are formed. But when I take phosphorus, phosphorus outer configuration is 3p3. Similar to nitrogen, even phosphorus has three unpaired orbitals, 3 unpaired electrons also. But this phosphorus is unable to involve in sidewise overlapping. See, this is 3p orbital. This is 3p orbital. Large size. When orbital size is more, the distance between the two orbitals is more. They are unable to form strong pi bond. Means the pi bond formed in between the p orbitals is very, very, very less. I mean very, very, very weak. Simply, in simple words, pi bond cannot be formed in between two 3p orbitals. Between 3p orbitals, there is no pi bond formation. So phosphorus is unable to form pi bonds, but nitrogen is able to form pi bonds. This is the reason why nitrogen exists in diatomic state and phosphorus exists in tetraatomic state. So in simple words, nitrogen exists in diatomic because it can have pi bond formation or multiple bond formation. But phosphorus is unable to form pi bonds. So one phosphorus cannot combine with another phosphorus with multiple bonds. So that's why P2 cannot be formed. Phosphorus is combining with other phosphorus atoms and existing in P4 state. Right. Same reason is applicable for oxygen and sulfur also. Oxygen has 2p orbital. 2p orbital is involving in bonding. So this 2p can form pi bond. Oxygen can exist as O2. But sulfur has 3p orbital. 3p pi bond formation does not take place. So it can't form S2. So sulfur is combining with other sulfur atoms through single bond and gives S8 molecule. So one is able to form pi bonds, another one is not able to form pi bonds. This is the main reason. Next, here the large difference between melting and boiling points of oxygen and sulfur is their atomicity. Right. Large difference between melting and boiling points of oxygen is atomicity. So suppose take oxygen. Oxygen atomicity is 2. Sulfur atomicity is 8. So as the molecular weight increases or molecular size increases, the van der Waals forces increases. Van der Waals forces directly proportional to their molecular weight or directly proportional to molecular sizes. See, oxygen molecular weight is 2 into 16. S8 molecular weight is 8 into 32. It has huge molecular weight compared to oxygen. So van der Waals forces increases, their melting and boiling points also increases. Right? So your boiling point depends on van der Waals forces, but melting point depends on intermolecular forces as well as their structure also. So in allotropic forms, we will see the structure of S8 molecules. Crystalline allotropes are there, we will see that. So here, according to NCERT, except nitrogen, all elements shows allotropy from the 15th group elements. In different books, differently given, but ultimately we need to follow NCERT. So except nitrogen, I mean nitrogen does not have allotropes. All other elements shows allotropy according to NCERT. Next, in 16th group elements, all elements shows allotropy. Next, coming to 17th group elements. In 17th group elements, all are diatomic X2. Here fluorine is pale yellow color, fluorine gas, yellow color. Fluorine and chlorine are gases, bromine is liquid, iodine is solid. So chlorine is greenish yellow. This is greenish yellow color gas. Bromine is orange red color. Iodine is violet black. Bromine is liquid, iodine is solid, fluorine, chlorine are gases. And they show colors. Fluorine is pale yellow color, chlorine is greenish yellow color, bromine is red color, and iodine is violet black color. Here, what is the reason for their color? So these molecules absorbs radiation from the visible light, and their electrons are excited to higher energy level. This is responsible for their colors. But why these molecules shows different colors means different molecules or different substances absorbs different frequency of radiation. Right? They don't absorb same frequency of radiation. Different molecules absorb different frequency of radiance and different transitions takes place. That's why they are showing different colors. So you can see the concept here. Next, another important point is bond dissociation enthalpy of halogens. So we know chlorine bond dissociation enthalpy is greater than bromine. Bromine and bond dissociation enthalpy is greater than fluorine. Fluorine is greater than iodine. So we expect fluorine with high bond dissociation enthalpy due to their small atomic size, but actually fluorine has less bond dissociation enthalpy, because what happened when fluorine is bonded with another fluorine, distance is less, that is correct, but each fluorine has 3 lone pairs. So lone pair repulsions are very high. The lone pairs are very close to each other, repulsions are more, the bond is going to break easily. So bond dissociation enthalpy order is what? Chlorine, next bromine, next fluorine, and next iodine. Next, there is solubility. Fluorine, chlorine react with water, and bromine, iodine, their reaction tendency is less with water, but they are sparingly soluble in water, very less soluble in water. But in organic solvents like chloroform, carbon tetrachloride, carbon disulfide, hydrocarbons, hydrocarbon means you can take cyclohexane as an example. Cyclohexane, hydrocarbon, one example. So bromine, iodine, less soluble in water and more soluble in organic solvents like chloroform, carbon tetrachloride, carbon disulfide, or cyclohexane. So they are soluble and they form colored solution. You can see here in this diagram, this chlorine is dissolved in the cyclohexane, so it is giving the colored layer. Bromine is giving colored layer. Iodine is also giving colored layer, right? But here water is also there. Aqueous layer means what? Water. So these halogens are not dissolved in water, but they are dissolved in what? Cyclohexane, and they are forming a colored layers at the top of the test tube. And this property is used in layer test. We will discuss in practical in organic chemistry, right? So these halogens are more soluble in organic solvent, first point. Halogens are less soluble in water, that is second point. And third point is this halogens forms colored solution with organic solvents, and it appears at the top of the test tube. Coming to 18 group elements, all 18 group elements are monoatomic. Helium, neon, argon, krypton, xenon, radon, oxygen, all are monoatomic. These elements are monoatomic. They are colorless, odorless, and tasteless, and very less soluble in water, and they have low melting and boiling points. Here, one interesting thing about helium. Helium has less boiling point, that is 4.2 kelvins, means minus 268.8 degrees Celsius. So you know minus 273 degrees Celsius means 0 kelvins. 0 kelvins temperature is called as absolute zero. 0 kelvins temperature is called as absolute zero. That is the least possible temperature. It is theoretically, it is possible. Practically, even today, we did not reach 0 kelvins temperature. No one has seen minus 273 degrees Celsius even for today. So that is theoretically, the least possible temperature is absolute zero, which is minus 273. Here, what I am trying to say, this minus 268.8 degrees Celsius temperature is close to absolute zero. That much lower boiling point is there for helium. Right, perfect. Now, at this temperature, this helium behaves as superfluid. It is called as superfluid. What is superfluid means? Its viscosity will be zero. At this temperature, that liquid, helium liquid has zero viscosity. So, why it is called superfluid? And what happened when its viscosity is zero means, you can see in this picture, the liquid helium rises through the walls of the vessel and it is coming down. It is flowing through the walls and falling down. So generally liquids won't rise up. Gases will have that property. Gases density is very less, they will rise. But here at the temperature, the liquid has the property to rise up. That's why it is called superfluid. At this temperature, its viscosity is zero. It is an unusual property. Next, coming to Allotropes of carbon. Carbon has many allotropes. Some are amorphous allotropic forms, some are crystalline allotropic forms. Amorphous means their atoms or molecules are not arranged in a systematic manner. If the molecules or atoms are arranged in a systematic manner, there is a particular arrangement. It may be simple cubic structure, face-centered cubic, or body-centered cubic, or hexagonal close packing, or any other structures. If the atoms or molecules are arranged in a particular method, that is called crystalline. So here we are going to discuss about crystalline allotropic forms of carbon. So crystalline allotropic forms: diamond, graphite, and fullerenes. First I am coming to diamond. Diamond is hardest substance on the earth. We know that. Because of its hardness, it is used as abrasive, and it is used in making dyes and making tungsten filaments. These are the applications. Now, this is diamond structure. So one carbon is bonded with 4 other carbon atoms. All valence electrons are involved in bonding. sp3 hybridization. Bond length is 154 picometers. No free electron. So diamond is a bad conductor or insulator. Diamond is bad conductor or insulator. Right? So it has, each carbon unit has tetrahedral structure. Each carbon unit tetrahedral. But the resultant structure of diamond is not tetrahedral. It has diamond cubic structure. Many tetrahedral units are joined together to give diamond cubic crystal. Simply we used to say DCC. What is this diamond cubic structure? It is same as FCC. Similar to FCC. So what is a similarity between FCC? In FCC, the atoms are present at corners and face centers. Right. In addition to the corners and face centers, if the atoms are present at tetrahedral voids, in case of diamond, half of the tetrahedral voids are occupied by carbons. All carbon atoms are occupied by carbon atoms. All face centers are occupied by carbon atoms, and 4 tetrahedral voids out of 8 are occupied by carbon atoms. Right? So the effective number of atoms per unit cell of diamond is 8. Right. So this is diamond cubic structure. This is the resultant structure of diamond. Because of this structure, the diamond density is very high, that is 3.51 grams per cc. Next, coming to graphite. This graphite has layer structure. Each carbon has 3 sigma bonds. 3 sigma bonds, only 3 valence electrons involved in this bond formation. So hybridization is sp2 and geometry is triangular planar. And bond angle is 120 degrees. This is perfect. But each carbon has 1 free electron. So this carbon, see the picture, this carbon has free electron and all these carbon atoms are having 1 free electron. Similarly, the other layer carbon atoms are also having free electrons. So 1 free electron involves in bonding with 1 free electron involves in bonding with other free electron. So this orbital and this orbital involves in sidewise overlapping, but distance is more. So due to more distance between the orbitals, a weak pi bond is formed. A weak pi bond. That bond can be called as pi bond, but it is not like normal pi bond. It's a weak pi bond. And this pi bond is not fixed. It is not fixed because due to less strength of these bonds, one layer slides on the other. When the top layer is sliding over the other layer, what happens? This bond is going to break and it will form a new pi bond with the other carbon atom. So right now it is in bonding here. When it is moving, the same carbon atom will form a bond with the other carbon atom like this. So overall, because of this structure, it has slippery nature and soft nature. So graphite hybridization is sp2. Cc bond length is 141.5 picometers and its density is less, that is 2.3 grams per cc. The resultant, each carbon unit is triangular planar, but the whole structure of graphite is hexagonal layer structure. And because of this layer structure, it has slippery nature and it is used as dry lubricant. So best example for dry lubricant is what? Carom board. So before applying the caroms, we have to spread some powder. What is a powder? Lubricant. So similar to the carom board powder, here graphite powder is used as a lubricant, where it is used generally in some industries where high temperature is there. So we cannot use liquid lubricants. At that temperature, the liquid is going to vaporize. So graphite, we are using graphite. Graphite boiling point is very high. It won't vaporize. So graphite powder is used in the industry where lubricants are required with high temperature. Next, coming to the important allotrope of carbon, fullerenes. These fullerenes are having even number of carbons, even number of carbons. What I mean to say, it can be C60 or C70 or C350 or any. So many types of fullerenes are observed. Among all, C60 is called Buckminster fullerene. C60 is called Buckminster fullerene. Right. In this C60, 20 hexagons are there and 12 pentagons are there, and total we have 32 rings. Total 32 rings. This hexagon and pentagon rings are fused with each other. So total 32 rings are there. Right? In this fullerenes, carbon-carbon bond length is, it has a single bond and double bond. So single bond is 143.5 picometers and double bond is what? 138.3 picometers. So, and there is a conjugation also. Single bond, double bond, single bond, double bond, single bond. This is what we call conjugation. So in fullerenes, conjugation is there. Single bond, double bond, conjugation is there. And delocalization is there. Delocalization is there. So resonance is there. And finally, the fullerenes are aromatic in nature. Fullerenes are aromatic in nature. They have aromaticity. And because of this aromaticity, they don't have dangling bonds. So that's why fullerenes are the most pure allotropic forms of carbon. So what are these dangling bonds? For example, let us take a substance, any one substance. Take this substance. Just break this substance into two halves. This is just for our understanding what is dangling. Break this substance into two parts. So when we break it, at the surface, new surface, all the bonds are broken. Means one side the bonds are broken, other sides bonds are there. So the bottom side bonds are there, but upper side there is no bond. Means all the molecules at the surface are experiencing residual forces or unbalanced forces. They are experiencing the unbalanced forces. Means their valence is not satisfied. So they are ready to form a new bond. So because of these unbalanced forces, all the molecules at the top of the surface attract the molecules available in the atmosphere. They form a temporary bonds. It may be oxygen molecule or nitrogen molecule or any dust particle. Whatever the molecule is available, the upper surface molecule are ready to mingle with those molecules. So temporarily some bonds are formed. Means some impurities are injected because of these unbalanced forces. Now coming to the fullerenes. This carbon, each carbon has 3 bonds only. One has free electron. That free electron is involved in resonance and it has aromaticity. Now break this fullerene. What happens? Free electrons are created. Old bonds are broken, free electrons are created. And these free electrons, again, they participate in the resonance and aromaticity. That's why they don't form any temporary bonds with atmospheric molecules. Right? So those temporary bonds are called dangling bonds, and fullerenes don't have to form any temporary bonds. So they don't form dangling bonds and they are the most pure form of carbon. Next, in this allotropes, among all the allotropes of carbon, graphite is thermodynamically stable. Kinetically stable allotrope of carbon is diamond. thermodynamically stable allotrope of carbon is graphite. And graphite is considered as standard allotrope. At standard conditions, standard heat of formation of graphite is what? 0. Diamond is not 0, fullerene is not 0, only standard allotrope. Graphite is considered as standard allotrope and its heat of formation is 0. So in jewelry, diamond's quality is measured in carats. What is that? 1 carat is equal to 200 milligrams. This point is important. And diamond standard heat of formation is what? 1.90. And fullerene's standard heat of formation is what? 38.1. And graphite is what? 0. Next, coming to allotropes of phosphorus, white phosphorus. So already we discussed one phosphorus cannot form multiple bonds with another phosphorus. So pi bond cannot be formed, only sigma bond is formed. That's why 4 phosphorus atoms combine to give tetrahedral structure. So white phosphorus is translucent white waxy solid and it is poisonous, insoluble in water, but soluble in phosphorus is soluble in carbon disulfide. It glows in dark and less stable, more reactive. That is due to angle strain. You can say ring strain. You can say ring strain or angle strain. So what is this ring strain and angle strain? Phosphorus has sp3 hybridization. sp3 hybridization means the expected bond angle is 109 degrees to 8 minutes. But here, how much bond angle we observed? Actual bond angle is 60 degrees. In white phosphorus, bond angle is what? 60 degrees. Actual bond angle is just 60 degrees. But expected bond angle is what? 109 degrees. So there is a large difference. So due to large difference between expected and actual bond angle, that structure, that P4 structure, tetrahedral structure is unstable for phosphorus. So easily it is going to break. It is more reactive, less stable. So how much more reactive, how much less stable means this white phosphorus at room temperature conditions, even in the dark, reacts with oxygen and produces P4O10. In its formation, it produces some light also. It will produce the light, but it does not have heat. Right? So that is called chemiluminescence. So some years back, many people thought that this light is considered as a ghost. So ghost light. So we don't have any ghost. We don't have any evil. Right? So in burial ground, the phosphorus present in the bones, when it is exposed to the atmosphere, it burns with oxygen and produces P4O10. During the process, it produces a light, but it won't have heat. That light only considered as ghost light. That is what chemiluminescence, not ghost. Next, this white phosphorus reacts with sodium hydroxide. With boiling sodium hydroxide, it produces phosphine and sodium hypophosphite. This is a disproportionation redox reaction. Disproportion redox reaction. Here phosphorus oxidation rate is 0, here -3, and this phosphorus is +1. 0 to -3 and 0 to +1 disproportion. Whatever it is, this phosphorus can react with sodium hydroxide. Red phosphorus does not react with any OH. Red phosphorus at room temperature does not react with oxygen. Red phosphorus is stable compared to white phosphorus. Now, I'm coming to red phosphorus. Here, red phosphorus, 1 unit of tetrahedral structure is 1 unit of phosphorus is combined with another phosphorus through sigma bond. So it has a polymeric structure. Because of polymeric structure, it is stable and less reactive compared to white phosphorus. So this red phosphorus has iron gray luster. Iron gray luster means the shining property is there. No odor, non-poisonous. White phosphorus is poisonous, red phosphorus non-poisonous. It is insoluble in water and carbon disulfide. Because of its polymeric structure, it is insoluble in water, insoluble in carbon disulfide. It does not glow in dark because no reaction with oxygen. So no reaction with NaOH. Next here, very important point is when white phosphorus is heated at 573 Kelvin's temperature, red phosphorus is formed. Perfect. When red phosphorus is heated under high pressure, a series of phases of black phosphorus is formed. So a black phosphorus is formed, right? Here we have two black phosphorus. One is alpha black and another one is beta black. So how this alpha black is formed? Alpha black phosphorus is formed. So alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803 kelvins. This alpha phosphorus can be sublimed in air, does not oxidize in air. It has opaque and monoclinic rhombohedral crystals. So how this beta black is formed? Beta black phosphorus is formed by heating white phosphorus at 473 kelvins under high pressure. So it does not burn in air up to 673 kelvins. So after 673 kelvins, it burns with oxygen and produces its oxide. So among all allotropic forms of phosphorus, thermodynamically stable allotrope is what? Black phosphorus. Sorry, red phosphorus. Thermodynamically stable allotrope of phosphorus is red phosphorus and standard allotropic phosphorus is white phosphorus. White phosphorus is considered as standard allotrope. So majority of the students doubt is, sir, red phosphorus is thermodynamically stable, then red phosphorus should be standard allotrope. Why white phosphorus is taken as standard allotrope? Simple reason is stability is a different thing and standardization is different thing. Standardization is arbitrarily. There is no specific reason. Here the reason is the ease of formation of white phosphorus is more. Due to more ease of formation of white phosphorus, the white phosphorus is considered as standard allotrope, but stable allotropic form is red phosphorus. The standard heat of formation of white phosphorus is 0, but red phosphorus is not 0. Only in standard state, heat of formation is 0 at standard conditions. Next, I am coming to allotropes of sulfur. Sulfur has two allotropes, alpha sulfur, beta sulfur. Rhombic sulfur is alpha sulfur, monoclinic sulfur or prismatic sulfur or beta sulfur. Different names are there. When rhombic sulfur is heated at 369 kelvins temperature, when rhombic sulfur is heated at 369 kelvins temperature, it converts into monoclinic. When monoclinic is cooled below 369 kelvins, means below 36 degrees Celsius, below 96 degrees Celsius, it converts into rhombic. So the temperature at which one allotropic form is converted into another allotropic form is called transition temperature. This 96 degrees Celsius is called transition temperature of alpha and beta, alpha sulfur and beta sulfur. Anyway, coming to some important points of alpha and beta sulfur. So alpha is yellow in color, melting point is 385.8 kelvins, density, specific gravity is 2.06, here specific gravity is 1.98. Beta sulfur specific gravity is 1.9. Specific gravity means it's a density. The relative density of solid is called specific gravity. Relative density of liquid is called vapor density. Absolute density means simply we call it as density, but relative density of solids and liquids is specific gravity. Relative density of gases is what? Vapor density. Right. So rhombic crystals, how these rhombic crystals are formed? Rhombic crystals are formed. First, we have to dissolve the roll sulfur in carbon disulfide. So dissolve the roll sulfur means sulfur sticks. The sulfur sticks, it may be amorphous form. The sulfur sticks are dissolved in carbon disulfide and they are allowed for evaporation. After complete evaporation, some crystals of sulfur crystals are formed. Those crystals are rhombic crystals. And how this beta sulfur is formed? This, take molten sulfur. When sulfur is heated at high temperature, it will come to liquid state, that is molten sulfur. Take this molten sulfur in a bowl. This is allowed for evaporation. And when solid crust is formed at the top, and make some holes at the bottom of this vessel, remove the liquid here, remove liquid and remove this crust. After removal of this crust and the liquid, the solid absorbed in this bowl is what? monoclinic sulfur. It has needle shape. So this is called needle shaped sulfur. You can see in this picture. This is sharp edge. The molecules are having sharp edge. Both are crystalline, and this is acid and this is also acid. Rhombic sulfur has acid molecules. Monoclinic sulfur has acid molecules, but their crystalline structure is different. So once again, how this alpha sulfur is formed? So dissolve the roll sulfur in the carbon disulfide. It is soluble in carbon disulfide but insoluble in water. So allow for evaporation. After evaporation of total CS2, the crystals observed in the dish, the crystals observed in the vessel is alpha sulfur. How beta sulfur is formed? This sulfur is heated at high temperature, you will get molten sulfur. The molten sulfur is allowed for evaporation. So after cooling, one solid crust is formed at the top. If any unsolidified substance is present in the vessel, make some holes at the bottom and remove that liquid and remove the crust. The crystals left in that vessel are monoclinic sulfur. They have sharp edge, so we used to call needle shaped sulfur or monoclinic sulfur. So this is acid and this is also acid, but this acid molecules arrangement is different. You can see the difference in arrangement of acid molecules for rhombic and monoclinic sulfur. Next, when this sulfur is heated, acid rings are heated at high temperature, you will get chair form. Actually, here we should have S6. When S8, suppose for example, this is alpha sulfur heated at 96 degrees Celsius, we will get beta sulfur above 96 degrees, and still heat this, we will get S6, we will get chair form, and S6 is converted into S4 on heating, and finally above 1000 kelvins temperature, we will get S2. So this is a crown shape or puckered ring structure or crown shape of acid molecule, and this is chair form of acid molecule. Right. When the sulfur is heated above 1000 kelvins temperature, you will observe S2. This S2 is paramagnetic in nature. So how do you say paramagnetic nature? Means by comparing with oxygen. So according to molecular orbital theory, MOT, oxygen is paramagnetic nature. So same as O2, S2 is also taken as paramagnetic in nature. Right? These are the details about allotropic forms of sulfur. Next, oxygen has two allotropes, ozone and oxygen. So oxygen we know. Coming to the ozone structure. So here this ozone has bent structure or angular structure. Bond length is 127.8 picometers. So if I take the structure like this, maximum covalency of oxygen is 3. In rare cases it is 4. Normally it won't be 4, it is 3. So in this structure you can see one side single bond, another side double bond. But even though it has single bond, double bond, bond length is single. That is what? 127.8 picometers on both sides because of the resonance. Single bond, double bond. Resonance is there. Due to resonance, all the two oxygen bonds are equivalent. Due to resonance, the two oxygen bonds are equivalent. Their bond lengths are same. So 127.8 picometers is there. And what is the bond angle? 116.8 degrees. So this is the resonance hybrid structure, and these two are resonating structure, canonical forms or resonating structures. So ozone has two resonating structures, and the bonds are involved in resonance. Two oxygen bonds are equivalent, and oxygen bond length is 127.8 picometers, and its bond angle is 116.8 degrees. Now coming to the most important part of P block trends: atomic radius, ionization enthalpy, electron gain enthalpy, electron negativity, right? And some other properties like their density, melting point, boiling point. These trends are important. So before going to trends, one important point as per the NCERT. So here 13th group element boron is a non-metal, remaining all elements are metals. In 14th group elements, carbon and silicon are non-metals, remaining germanium is metalloid, tin, lead and flerovium are metals. So here we have an ambiguity. Carbon is non-metal, it's perfect, but silicon is metal, silicon is non-metal or metalloid. See, in NCERT periodic table, periodic classification of elements, one periodic table was given. In that periodic table, silicon is mentioned as metalloid. It's fine. But if you study 14th group elements NCERT textbook clearly mentioned it as non-metal. Silicon was given as non-metal in the 14th group elements. So of course, silicon has metallic properties and non-metallic properties, but comparatively, non-metallic properties are more for silicon. So silicon is a non-metal. From many reference books, I have seen silicon is non-metal. Metallic properties also there, but predominantly it has more non-metallic character. The evidence is NCERT, which is given in the physical properties of 14 group elements. So here I will take silicon as non-metal. So what are the metalloids given in the NCERT as per the what are the metalloids given in the NCERT? So germanium is metalloid, arsenic is metalloid, antimony is metalloid, selenium is metalloid, tellurium is metalloid, astatine is metalloid. So all elements above these metalloids are non-metals, below these metalloids are metals, right? The majority elements in the periodic table are metals. Maximum percentage metals. Now I'm coming to the P block trends. So you can see one statement on the screen. This is from NCERT, one of my favorite statement. The variation in the properties of P block elements due to influence of D and F electrons. The variation in the properties of P block elements due to influence of D and F electrons in the inner core of heavier elements makes their chemistry interesting. Means generally atomic radius means what? Down the group increases. Ionization enthalpy is what? Down the group decreases. But these trends are not always perfect. In some cases, there are some exceptions. So whatever the exception you observed in the P block, it may be boron family or carbon family or nitrogen family, whatever the exception you have seen, that exception is coming at the bottom of the group. Means those exceptions are coming at heavier elements. Why these exceptions are seen at heavier elements? Because in the heavier elements, there are many D electrons and F electrons. So D and F electrons are having poor shielding effect, very less shielding effect. Because of this poor shielding effect of D and F electrons, there are some changes in the radius, changes in the electronegativity, changes in the ionization enthalpy. In simple terms, whatever the exception we have seen in the P block elements, that exception is coming at heavier elements. That exception is due to poor shielding effect of D and F electrons, right? In simple words, it may be lanthanide contraction or inert pair effect. Finally, it is connected with the lanthanide contraction and it is connected with the inert pair effect. So inert pair effect is also one of the consequences of lanthanide contraction. There are many consequences for lanthanide contraction. So inert pair effect is also one of the consequence of lanthanide contraction. So first of all, what are the lanthanides? In this periodic table, you can see from cerium to lutetium, 14 elements, lanthanides. Here, electrons are going to 4f orbital. From thorium to lawrencium, actinoids. Here, differentiating electrons are going to 5f subshell. Of course, some exceptions are there. Always the electron is not going to 4f and 5f. Some exceptions are there. So we will see in the separate topic. This lanthanum belongs to D block element, actinum belongs to D block element. After lanthanum, 14 elements are lanthanides. After actinum, 14 elements are actinides. Now, here in lanthanides, the electrons are going to 4s subshell. 4f electrons shielding effect is very less. When shielding effect is less, nuclear force of attraction increases on the outermost shell. So there is a strong nuclear force of attraction in the outermost electrons. Therefore, what happens? The size gradually decreases. This is what we call lanthanide contraction. In a similar way, in the actinides, the differentiating electron, last electron is going to 5f subshell. F subshell shielding effect is very less. Then nuclear force of attraction on the outermost electrons increases. So that what happens? Actinide size also gradually decreases. This is what we call actinide contraction. But generally, we don't use actinide contraction as a specific term. So simply we will use lanthanide contraction. This lanthanide contraction explains lanthanide contraction itself and actinide contraction also. Now, exactly in simple words, what is shielding effect and what is effective nuclear charge and what is lanthanide contraction and then inert pair effect. First, we will see these topics. Then we will go to periodic trends. If you understand exactly what is shielding effect, nuclear charge, lanthanide contraction and inert pair effect, and it is easy to understand all the exceptions in the periodic trends. Right. Coming to shielding effect, it's very simple. This is our nucleus. Here, these are inner shells, any inner shells, and this is outermost shell. Consider it as outermost shell. Now, the nucleus is trying to attract the inner shell electrons and outermost shell electrons also. So when nucleus is trying to attract the outermost electrons, or inner electrons are shielding the outer electrons. They are hiding the outermost electrons. So they are not allowing the nucleus to attract the outermost electrons. For example, if this element is calcium, this element is calcium. Calcium has 20 protons, means 20 units of nuclear charge is there. So what we expect 20 units of positive charge is acting on each and every shell. But actually what happened? 20 units of positive charge is not acting on the outermost shell because the inner electrons are decreasing the nuclear force of attraction on the outermost shell electrons. The inner electrons are acting like a wall in between nucleus and outermost shell. That's why nuclear charge decreases. So due to shielding effect, there is some reduction in the nuclear charge on the outer electrons. So different shells electrons will have different nuclear charge. So the resultant nuclear charge is called effective nuclear charge. So what I am trying to say, in calcium we have 4 shells. So all the 4 shells are not having same nuclear charge. First shell is having more nuclear charge, second shell gradually decreases, third shell decreases, and fourth shell very less compared to others. So why there is gradual decrease in nuclear charge from lower shell to higher shells? Due to shielding effect. So due to shielding effect, the resultant nuclear charge acting on the outermost electrons is called effective nuclear charge. And how do we calculate this effective nuclear charge? We have a formula. Z effective is equal to Z minus S. So effective nuclear charge is equal to its nuclear charge. If it is calcium, 20 units of positive charge. And screening effect by using Slater rules, you can calculate the screening constant. So Z minus S gives us effective nuclear charge. Next, coming to lanthanide contraction. This is very important topic, very important point. In short way, we will discuss. In lanthanides, electrons are going to 4f subshell. So these 4f electrons are ineffective in shielding. Poor shielding effect is there. Then what happens? Nuclear force of attraction is very high on the outermost shell. What is the outermost shell for lanthanides? 6s. So in lanthanides, the nucleus is strongly attracting the 6s outermost shell. So the size decreases. So cerium to praseodymium to neodymium to promethium, gradually the size decreases. This contraction in size, this reduction in size is called lanthanide contraction. Same thing is observed in actinides also. Here, the most important point is lanthanides common oxidation state. All lanthanides common oxidation state is +3. You can see Ce3+2, Lu3+. So there is a gradual decrease in ionic size from cerium to lutetium. So their common oxidation state is +3. Their ionic form is +3, Ce3 plus, Pr3 plus, like this. So Ce3 plus to Le3 plus, there is a gradual decrease in size. So ionic radius gradually decreasing. But when we come to their elements, the decrease in atomic size is not continuous. There is no gradual decrease in the atomic size in lanthanides. So there is a sudden rise in, means abnormal atomic size in the europium and abnormal atomic size at ytterbium. Right? According to lanthanide contraction, from one element to next element, there should be gradual decrease in atomic size. But in the ions of lanthanides, there is a gradual decrease in size. But in elements, there is no gradual decrease in size. So where no decrease in the size, europium and ytterbium. The first point is, among all lanthanides, which has highest atomic radius? Europium. The highest atomic radius is europium. So why europium has higher atomic radius? Why there is no decrease in atomic radius? Means in europium, the differentiating electron is going to 4f subshell. Means it will get 4f7 configuration, half-filled configuration. This is stable configuration. Half-filled configuration is stable. So generally in lanthanides, three electrons involved in metallic bonding. 3 electrons involved in metallic bonding. Each atom is giving 3 electrons. So, but in case of europium and in case of ytterbium configuration is fully filled configuration, that is 4f14. 4f14 is fully filled configuration. This is also stable configuration. So in all lanthanides, 3 electrons are involved in metallic bonding. In case of europium and ytterbium, only 2 electrons are participated in the metallic bonding. In europium and ytterbium, just 2 electrons are involved in bonding. So why only 2 electrons? In lanthanides, in other lanthanides, 2 s electrons in general I am speaking. 2 s electrons, 1 f electron is participated. But in case of europium and ytterbium, only 6 s electrons, 2 electrons are participated in the metallic bond formation. F electrons are not involved because they have stable configurations. So number of electrons per atom involved in the metallic bond is less in case of europium and ytterbium. So metallic bond is weak. So the size is not reduced. The size is higher. Relatively, europium and ytterbium have higher atomic radius because only 2 electrons are involved in metallic bonding instead of 3 electrons. Right? I hope you understood this. Then why europium has more atomic radius than ytterbium? The simple reason is, this is europium. Ytterbium is second last element. Second last element means the number of protons are more compared to europium. Ytterbium has more number of protons, so more nuclear charge. So due to more nuclear charge, ytterbium atomic radius is less compared to europium. This is the reason why the radius decreases from left to right. So left to right, number of protons increases, effective nuclear charge increases, size decreases. Same reason. Europium, ytterbium reason is same. Right? I hope it is clear. Once again, the important points I will revise here. Due to lanthanide contraction, ionic size gradually decreases from Ce3 plus to Le3 plus. There is no exception. In case of elements, there is no steady decrease in atomic radius. We observed the abnormal atomic radius at europium and ytterbium. That is because of their fully filled and half-filled configurations, which is connected to the metallic bonding. The largest atomic radius element in the lanthanides is europium. Next element is ytterbium. The largest ionic size element in the lanthanides is what? Ce3 plus. Right. Now coming to the consequence of lanthanide contraction. So due to lanthanide contraction, 4D, 5D series elements sizes are approximately equal. Example, zirconium and hafnium, size approximately equal. And these are approximately equal to 6D series also due to actinide contraction. And other important consequence of lanthanide contraction is inert pair effect. Inert pair effect. So, due to lanthanide contraction, there is a higher effective nuclear charge in the lanthanides. So, this effect is continued in the D block elements. So, after lanthanides, the next elements are what? D block elements. And after D block elements, next elements are what? P block elements. This effect is continued in the P block elements also. What I am trying to say, due to lanthanide contraction, there is a strong nuclear force of attraction in the P block elements also, especially the heavier P block elements. So due to strong attraction force, outermost S electrons are unable to participate in the bonding. So when S electrons are not participated, they can't show higher oxidation state. They show only lower oxidation state. So in P block, 13, 14, 15th groups, last elements, lower oxidation states are stable compared to higher oxidation state. That is because of inert pair effect. This inert pair effect is one of the consequences of lanthanide contraction. And third consequence is ionization enthalpy. Ionization enthalpy of gold is greater than copper and copper is greater than silver. I mean, this 5D series elements ionization enthalpies are greater than 3D and 3D series ionization enthalpy is greater than 4D. Generally, what we expect down the group decreases. But here, 5D series ionization enthalpy is greater than 3D, 3D ionization enthalpy is greater than 4D. This is also because of lanthanide contraction. Due to lanthanide contraction, in the heavier elements, there is strong nuclear charge, higher effective nuclear charge. Because of that higher effective nuclear charge, 5D series elements ionization enthalpies are higher than 3D and 4D. So these are the some important consequences of lanthanide contraction. Now, exactly what is inert pair effect means? Just now we discussed the NS electrons won't participate. NS orbital electrons are unable to participate in the bonding. So, NS2, NP, 1 to 3 I'm taking. Means 13th group elements, 14th group elements and 15th group elements. So in 13th group elements, so this inert pair effect is observed in only these three groups. When NS electrons are not participated, 13th group elements, only one electron is involved. From 14th group, only 2 electrons are involved. From 15th group, 3 electrons are involved. So therefore, 13th group shows only +1 oxidation state. 14th group last element shows +2 oxidation state. 15th group last element shows +3 oxidation state. So this is a result of or effect of lanthanide contraction. You can see in this picture, all elements are stable at +3 in boron family, but thallium +1 is more stable compared to Tl3+. In 14th group elements, all elements are stable at +4, but lead last element +2 is more stable than +4. In 15th group elements, all elements are stable at +5 oxidation state. Remember, oxidation state is different, valency is different. Valency is always real. Oxidation state can be real or imaginary. Both cases are there. We will see that. So bismuth is more stable at +3 because of inert pair effect. One important application of this inert pair effect is if I take the compound PlCl3, PbCl4, and BiCl5. Actually, they are very unstable. They do not exist. Suppose these compounds are given. TlCl3, it is in +3 oxidation state. PbCl4, it is in +4 oxidation state. BiCl5, it is in +5 oxidation state. They are very, very, very unstable. So this TlCl3 undergoes reduction to form Pl+. PbCl4 undergoes reduction to form Pb2+. And BaCl5 undergoes reduction to form Ba3+. So all are going for reduction to get their stable oxidation state. So the compounds which undergoes reduction acts as oxidizing agent. So hypothetically, any thallium compound is given with +3, lead compound is given with +4, bismuth compound is given with +5, those compounds acts as oxidizing agent because they undergoes reduction to form stable oxidation state. This is one of the important application of inert pair effect. Now coming to the important part, trends. So as we discussed, the starting statement says that whatever the exception you have seen in the p block elements, 11th p block or 12th p block elements, directly or indirectly, who is responsible? Lanthanide and contraction. Pore shielding effect of d and f electrons is responsible for any irregular trend in the p block. So now see atomic radius. So all families atomic radius is given. Here in 13th group boron family, we expect down the group atomic radius increases. But the exception is what here? Aluminium, gallium. Aluminium atomic radius is greater than gallium. That is due to pore screening effect of d electrons. There are 10 d electrons. Their shielding effect is less. Effect is less means they are not hiding. They are not covering the outermost electrons properly. Then effective nuclear charge increases. The size decreases. In gallium, this is in case of gallium. So due to pore shielding effect of d electrons and higher effective nuclear charge, gallium size is reduced and which is less than aluminium. So in boron family we observe this irregularity. Yes, coming to carbon family, so there is no exception, down the group increases. Nitrogen family, no exception, down the group increases. Oxygen family, no exception, down the group increases. Halogens, no exception, down the group increases. Noble gases, down the group increases. Now I am coming to ionic radius. Ionic radius. So here boron family, generally their common oxidation state is what? +3. Even thallium also I am taking +3. Aluminium 3+2, thallium 3+. I mean down the group ionic radius increases. There is no exception in that. Right. So here one interesting point regarding boron. What is it? Take boron. Boron configuration is 1s2, 2s2, 2p1. Right. So to get boron 3+ oxidation state, I should remove 3 electrons. For the removal of 3 electrons from the boron, we need very high ionization enthalpy. Practically, it is impossible. That much amount of energy is very difficult to supply to remove 3 electrons from the boron. So boron does not exist in B3. Theoretically, we used to write B3+ like that. But practically, B3+ ion does not exist. Why B3+ ion does not exist means the simple reason is IE1+, IE2+, IE3. So the total ionization enthalpy is very high, which cannot be given practically. So that's why here B+ only represented, B3+ not represented. Generally, students' doubt is, sir, BCl3 is there. In BCl3, boron oxidation state is +3. Then why don't you write +3? You are saying that B3+ does not exist. But here in BCl3, boron oxidation state is +3. So these are imaginary oxidation state. Here boron is sharing 3 electrons with 3 chlorine atoms. It is not losing electrons. If any particular element is written in the ionic state means it has to lose electrons. But here hypothetically we are writing +3 oxidation state. Oxidation state can be real or imaginary. In case of ionic compounds, oxidation state is real. In case of covalent compounds, oxidation state is hypothetical. So based on the electronegativities, we are assigning oxidation state. Right? For non-metals, I mean higher electronegative elements, oxidation state negative. Lower electronegative elements, oxidation state is positive. Like that, we are assigning the oxidation state. But in covalent compounds, there is no real plus or real minus. There is only sharing of electrons. I hope you understand that. So B3+ ion does not exist. Why? The sum of the first, second, third ionization enthalpy values are very high. So B3+ does not exist. The same concept is applicable for C4+ also. C4+. Removal of 4 electrons from the carbon is very difficult. Its ionization enthalpy is very high. C4+ does not exist. But there are so many compounds, covalent compounds with +4 oxidation state. That's a different case. Now, So here no exception, silicon, germanium, tin, lead in +4 state, +2 state, there is no exception. In 15th group, one very interesting point is arsenic, phosphorus, nitrogen. They have more electronegativity, nitrogen, phosphorus, arsenic. First three elements, electronegativity is more, so the negative oxidation state. Nitride, phosphide, arsenide. Bismuth, antimony, metallic nature is more, so we have to take their positive oxidation state. These are cations and these are anions. So whenever you compare anions atomic size with cations, no, anions atomic size is more. So especially for isoelectronic species, these are not isoelectronic species, they are based on the values. Now generally I am speaking isoelectronic species, anion size is greater than neutral, neutral size is greater than cation. When positive charge increases, size decreases, negative charge increases, size increases. So N3 minus, P3 minus, ES3 minus, they are anions, their size is more than cations, Bi3 plus and Sb3 plus. This is one important thing. It is clearly mentioned in the NCERT. Next, oxygen family and halogen family, right? Down the group, ionic size increases. Size, there is no exception, right? Now coming to ionization enthalpy. So boron family and carbon family, two exceptions are there. Ionization enthalpy. Others down the group decreases. Ionization enthalpy decreases. Top to bottom, ionization enthalpy decreases. So in boron family, thallium has the higher ionization enthalpy. Why thallium has higher ionization enthalpy means? So same reason, lanthanide contraction means electrons are in the f orbital. Pore screening effect, higher effective nuclear charge. So ionization enthalpy increases. We discussed about gold. Why gold has higher ionization enthalpy? In gold, 5D series elements, electrons are in the f orbital. So pore screening effect, higher effective nuclear charge and higher ionization. Similarly, thallium has higher ionization enthalpy compared to other elements except boron. So due to the changes in the effective nuclear charge, we observed an exception in the boron family and carbon family. So here thallium, gallium, aluminum, indium, so exceptional order. In carbon family, we expect lead should have lowest ionization enthalpy, but due to the same reason, lead has higher ionization enthalpy than tin. Only these two exceptions. In all other groups, down the group increases. Down the group decreases. Ionization enthalpy decreases. In all other groups, ionization enthalpy is inversely proportional to size. So we observe these two exceptions. Coming to electronegativity. Even for electronegativity, same reason. Pore shielding effect of F electrons and pore shielding effect of D electrons. So increase in effective nuclear charge. Whenever there is an increase in effective nuclear charge, their electronegativity increases. Ionization enthalpy increases. So we observed three exceptions. Boron family exception is the boron, thallium, indium, gallium, aluminum. This is the decreasing order. In carbon family, electronegativity decreases. Carbon, lead, silicon. And important point is what? Silicon, germanium, tin electronegativities are equal. Next, nitrogen, phosphorus, arsenic decreases. So electronegativity down the group decreases. Down the group, electronegativity decreases. This is our expectation. But here silicon, germanium, tin are equal and antimony, bismuth are equal. In others, no exception. Oxygen to tellurium electronegativity is decreasing and fluorine to iodine electronegativity is decreasing. And the most important point is noble gases. Noble gases do not attract electrons because already they have stable configuration, either duplet or octet configuration. So they don't have any tendency to gain electrons, to attract the electrons. So electronegativity of noble gases is considered as 0. So remember, electronegativity is a relative value. It does not have any particular unit. It is not energy. It's a relative value compared to others. So noble gases do not have any tendency to attract the electrons, to attract the shared pair of electrons. So electronegativity of all noble gases is considered as 0. Coming to electron gain enthalpy. when an electron is inserted in the outermost shell of any neutral gaseous atom, some amount of energy is released in general. So how much amount of energy is released? That is what we call electron gain enthalpy. So generally, this electron gain enthalpy is inversely proportional to size in general. So down the group, this electron gain enthalpy decreases down the group. But there are some exceptions. Right. So first we will see these exceptions and some other important points are there. We will see all. Here, in 16th group elements, oxygen has least electron gain enthalpy. So electron gain enthalpy means that is a negative enthalpy value. I am talking about negative enthalpy. Energy released means negative. Energy absorbed to insert an electron is positive enthalpy. I am talking about negative enthalpy. Sulfur to selenium, selenium to tellurium, tellurium to polonium, electron gain enthalpy decreases, and oxygen has the least electron gain enthalpy. The reason is oxygen is very small in size. When an electron is added, already oxygen has 6 electrons in its outermost shell. Now I am adding one more electron. So 7 electrons are present in a small region. So electron repulsions are more. Due to higher electron repulsions, its electron gain enthalpy is very less compared to others. So this is the reason for the statement. Generally, in all groups, second element electron gain enthalpy is more than first element. Fluorine, chlorine. So chlorine electron gain enthalpy is more than fluorine. Reason is same. Fluorine is small in size. Already 7 electrons are there. When 1 electron is added, total 8 electrons. When it gains 8 electrons, it will be stable. Even though due to small size, electron repulsions are more, the amount of energy released is less compared to chlorine. So in groups, why second element has higher electron gain enthalpy, more negative electron gain enthalpy than first element means their smaller atomic size and electron repulsions. So this is one point. Now, sir, you have written here 16th group elements and 17th group elements and inert gases only. Other groups, why you have not written? So 13th group, 14th group, 15th group, electron gain enthalpy values not given in NCERT. So we don't have any standard reference. So it's better to avoid. But in different materials, different books, different values are given. So one book, one order. Different books, different orders. Completely there is an ambiguity. So which is not given in the NCERT, they don't ask. So 13th, 14th, 15th group elements, electron gain enthalpy orders not required. They don't ask any question which that order or which has more, which has less. They don't ask. It is better to skip it. Instead of going for ambiguity, it is better to skip. We will not get any questions in that. Now, coming to noble gases. Noble gases, electron gain enthalpy value is positive. So, what is positive electron gain enthalpy? When electron is inserted, energy must be supplied. That is positive electron gain enthalpy. When energy is released with the insertion of electron in the outermost shell, that is negative electron gain enthalpy. There are few elements with positive electron gain enthalpy. They are noble gases. So noble gases and beryllium, magnesium, nitrogen. All noble gases, positive electron gain enthalpy. Beryllium due to 2s2 configuration. Magnesium due to 3s2 configuration. Nitrogen due to 2p3 configuration. Their electron gain enthalpy values are positive. Due to their stable configuration, when electron is added, they don't accept. When we try to add an electron, they don't accept. So forcefully we should insert an electron. Means energy must be supplied. They have positive electron gain enthalpy. In the total periodic table, the elements with positive electron gain enthalpy, beryllium, magnesium, nitrogen and noble gases. All other elements are negative enthalpy values. And next point is, among all elements except noble gases, beryllium, magnesium, nitrogen, remaining all elements, first electron gain enthalpy is negative. But if you come to second, third or fourth electron gain enthalpy values, that is always positive. Second electron gain enthalpy onwards, all are positive. Next, third point. Now, this is very, very, very important. Very important. Everyone concentrate. Fluorine, chlorine, bromine, iodine. I am asking electron gain enthalpy order. Electron gain enthalpy order is chlorine is greater than fluorine, fluorine is greater than bromine, bromine is greater than iodine. What it means, generally electron gain enthalpy mentioned means it is negative electron gain enthalpy. Sometimes in questions they will give clearly what is the negative electron gain enthalpy. In some cases they are not giving negative, even though you should understand that that is negative only, energy released. Chlorine is greater than fluorine, fluorine is greater than bromine, iodine. Suppose if the question is electron affinity, this order is wrong. Electron affinity order is iodine, bromine, fluorine and chlorine. So electron affinity is equal to minus of electron gain enthalpy. Means I am seeing the sign only, not exact relation. Exact relation you will study in the periodic table or you will study in the thermodynamics. Or electron gain enthalpy is a negative sign of electron affinity. So if the question is electron affinity, you should consider that opposite magnitudes. So electron affinity of halogens order is iodine greater than bromine, bromine is greater than fluorine, fluorine is greater than chlorine. But negative electron gain enthalpy or electron gain enthalpy means chlorine, fluorine, bromine, iodine. So what is the evidence for this? So you can see so many JEE mains questions. In JEE mains questions, they answered like this based on this concept, right? Now coming to density, there is no exception in the density. Density is equal to mass by volume. Density is mass by volume. When the rise in mass dominates the volume, density increases. The more increase in mass, less increase in volume, what happens? Density increases. In P block, there is no exception. Down the group, density increases. There is no exception in all the elements. Right. In 14th group elements, concentrate here. Lead highest, next tin, next germanium, next silicon, next carbon is there. So if you consider this carbon as graphite, it has the lowest density compared to other elements. But if you consider that carbon as diamond, this diamond density is greater than silicon. Germanium is greater than diamond, but diamond is greater than silicon. This is one important point here. Other elements down the group increases. Melting and boiling points. First of all, this melting point depends on intermolecular forces. Boiling point depends on intermolecular forces. And melting point depends on intermolecular forces and packing. This packing depends on, if they are metals, no, they depends on metallic bond. This metallic bond depends on number of electrons involved in metallic bonding. If more number of electrons involved in metallic bonding, stronger metallic bond, and the packing is more, melting point is more. If less number of electrons involved in the metallic bonding, packing is less, bond strength is less, and melting point is less. So melting point depends on so many factors, intermolecular forces, the packing indirectly depends on metallic bond. But boiling point depends on intermolecular forces. So this is purely memory based. There is no particular concept. There is no strict concept in that. So we need to practice all these orders. So I have given all orders here. Boron family, carbon family, nitrogen, oxygen, halogens, inert gases, all values based on NCERT values I have given this order. Now, standard reduction potential. So what is standard reduction potential? The tendency of an element to get reduction is standard reduction potential. the tendency of an element to get oxidation is standard oxidation potential. So according to IUPAC, only standard reduction potentials are followed. We don't discuss oxidation potential values. So we know that SRP is equal to minus SOP or SOP is equal to minus SRP. We can convert like this. But while we are explaining the concepts, we are following only standard reduction potential values. Now, when I take a metal, standard reduction potential, its standard reduction potential depends on three factors. In case of metals, that SRP depends on the heat of atomization or heat of sublimation, and it depends on the ionization enthalpy, sum of the total ionization enthalpy. And third point, it depends on its hydration enthalpy. So SRP of a metal depends on heat of atomization and ionization enthalpy and hydration enthalpy. That means first we have to break the given solid into individual atoms, and second we should remove n number of electrons, either 1 electron or 2 electron or 3 electrons, depends on the concept. And third, after removal of electrons, these ions are hydrated in the water, hydrated in the aqueous solution, some amount of energy is released. So the SRP value depends on these three factors. In case of non-metals, this SRP, standard reduction potential, depends on three factors again. Here, the first factor is bond dissociation enthalpy. So energy required to break the molecule into atoms. And second factor is electron gain enthalpy. How much amount of energy is released when an electron is added in that. And third point is hydration enthalpy. After formation of these anions, when these anions are taken in aqueous solution, so they get hydrated, they are stabilized, and energy is released. So non-metals SRP depends on bond dissociation enthalpy, electron gain enthalpy, hydration enthalpy, and metals SRP depends on heat of atomization or sublimation, ionization enthalpy, and hydration enthalpy. Now coming to the values. So in NCERT, 13th group elements, 17th group elements, SRP values are given. You can see those values on the screen. If I arrange these values from positive to negative, so positive value consider higher value and negative value consider lower value. If I arrange these SRP values in the decreasing order, from boron family, thallium to indium decreases, indium to gallium decreases, gallium to aluminum decreases. So this order is important. And what is this order? Plus 3 to plus m. Plus 3 to plus m. For example, the highest plus 3 to plus m reduction potential value is for thallium. What it means? Thallium has very high tendency to go from plus 3 state to elemental state. It has very high tendency to go from plus 3 state to elemental state. Means what it says, Tl plus 3 is unstable. So this SRP values tells us the stability of the oxidation states also. Here, high SRP for thallium from plus 3 to 0 means in elemental state only more stable compared to plus 3 state of thallium. So this is how SRP explains the stability. Next, halogens. See halogens. These are non-metals. Highest SRP for fluorine. And what is a SRP? M to M minus 1. So fluorine to F minus, the SRP value is 2.87. This is the highest SRP among all elements. Lowest SRP lithium, highest SRP fluorine. So these SRP values for non-metals depends on bond dissociation enthalpy, electron gain enthalpy, hydration enthalpy. For metals, it depends on heat of atomization, ionization enthalpy, and hydration enthalpy. Right. The resultant value is SRP. Coming to the point. So when fluorine is converted from elemental state to fluoride ion, its SRP value is highest 2.87. What it says, F minus is most stable for fluorine. Than elemental state, fluorine has more stability in the ionic state, F minus state. So this is how SRP explains the stability of the oxidation states, right? Next, boron family, other SRP values are given. These SRP values from +1 to +7. That order is aluminium to indium, indium to thallium, thallium to gallium decreases. This order is also important to us. Next, here one important point is gallium in acidic medium, its SRP value is -0.79. In alkaline medium, its SRP value is -1.39. So, in which medium gallium has higher SRP? Acidic medium. In which medium gallium has lower SRP? Basic medium or alkaline medium. Like that, they may ask questions. Statement type of questions or assertion reason type of questions. Like that, they may ask. So, this is a fact based on NCERT. Now, coming to oxidation states and covalency. So already we discussed oxidation state and valency are different things. Oxidation state either positive or negative or fractional or even zero also. But valency is always positive. Valency is always positive. It never be negative and never be fractional. Valency is real. Oxidation state may be real or imaginary. Right. For example, I am taking nitrogen. Nitrogen maximum valency is 4. It can form only 4 bonds. Covalency means number of covalent bonds formed by that particular atom. So maximum valency of nitrogen is 4. It can form 4 bonds. But maximum or highest oxidation state of nitrogen is what? +5. Highest oxidation state is +5. This is hypothetical. HNO3. In HNO3, if you go for calculations, nitrogen oxidation state is +5. N2O5, nitrogen oxidation state is +5, but it's not real. Based on the electronegativity, we are assigning +5. Right? I hope you understood the difference between oxidation states and covalency. Now coming to second period elements, third period elements, what are their common valencies and maximum valencies? See, any group, first group to fourth group, its common valency is group number. First group to fourth group, common valency is its group number. Next, fifth group, 15th group. 15th group to 18th group, its common valency is 8 minus group number. 8 minus group number. So, first group element, valency, common valency is 1. Second group 2, third group 3, fourth group 4, fifth group 8 minus 5, 3, sixth group 8 minus 6, 2, seventh group 8 minus 7, 1, and eighth group 8 minus 8, 0. This is the common valency. And maximum valency, coming to maximum valency, maximum number of bonds can be formed by that particular element. So lithium maximum valency is 1 only, but there is one exception. In dimerization in vapor state, it can go up to 2. Generally it is 1 only. It can form only 1 covalent bond, but there is an exception. In the vapor state, it will go for dimerization and it can give 2 also. That's why here star represented. Means rare cases. Rare cases it will show 2. Beryllium maximum 4. Its example is what? BeF4 2 minus. BeF4 2 minus. Here how many covalent bonds are there? 4 covalent bonds are there. Remember, coordinate covalent bond or dative bond is also one type of covalent bond included in the covalent bonds. So there are 4 bonds for beryllium with 4 fluorine atoms. So its maximum covalency is 4. So boron maximum covalency is also 4, BF4 minus. Example, there are 4 bonds. Their oxidation states are different. You can calculate mathematically oxidation states. Next, carbon maximum valency is 4. There is no expansion. So why carbon maximum covalency is 4 means there is no vacant orbitals. No vacant d orbitals. It can't extend valency up to beyond 4. So if you go to third period elements like silicon, phosphorus, they have d orbitals, 3d orbitals. So with excitation, they can extend their valency. So second period elements can't extend their valency, but third period elements can extend their valency by using vacant orbitals. So here 15th group elements, maximum covalency, 15th group elements, nitrogen maximum covalency is 4. So here these are all second period elements. First I am talking about second period element. So nitrogen maximum covalency is 4. Example, HNO3, 4 bonds are there. NH4 plus 4 bonds are there. Next, oxygen maximum covalency generally 3, but there is one exception, rare case up to 4. In NCERT also, oxygen maximum covalency is mentioned as 4. Let us follow 4 only. That example is B4OOAC 6. In this complex, oxygen valency is 4. So commonly the higher covalency of oxygen is 3 only, like H3O plus, here 3 only. But in this complex, it shows 4 valency, that is rare case. Next, neon 0. Second period noble gas element is neon. It does not have any compounds. Its valency is 0. Next, coming to third period elements. Third period elements can extend their valency by using the vacant orbitals. Sodium maximum valency is 1 only. Magnesium up to 6. Generally 4 it will show, but it can show 6 also. MgH2O6 2 plus, that is an example, right? In chlorophyll also it is 6, right? In NCERT it is mentioned clearly, MgH2O6 2 plus complex is formed with coordination number 6. Here covalency is 6. So aluminium AlF6 3 minus or AlH2O6 3 plus, here 6 coordinate covalent bonds are there, 6. 14th group maximum covalency 6, 15th group maximum covalency 6, 16th group maximum covalency 6, 17th group maximum 7, 18th group 0. Generally it is 0, but if I take xenon, in XeO4 there are 8 bonds. So for argon it is 0. So as we are discussing third period elements, third period noble gas element is argon. Argon maximum covalency is 0. But if I consider xenon 8 bonds it can form in XeO4, maximum covalency is 8. So this is about covalency. Oxidation states you can calculate mathematically. Now coming to anomalous properties. So anomalous properties, diagonal relationship is also one of the anomalous property. So what is this diagonal relationship? Second period elements from the first group, second period element shows some similarities with the second group, third period elements. This is observed for 3 groups, first group, second group and 13th group. We used to call it as third group, actually it is 13th group. First group, second period element have some similar properties with the second group, third period element, that is diagonal relationship. Here, diagonal relationship is due to 3 reasons. Similar atomic radius, I will give you an example also. Similar atomic radius, similar electronegativity or electropositivity, means their electronegativities are almost same because their sizes are almost same. So why their sizes are same? Their polarizing power is same. So polarizing power is charged by radius whole square is a polarizing power. Suppose if I take lithium Li plus and its diagonal pair Mg2 plus. So its charge by Mg2 plus radius whole square is approximately equal to lithium charge by its radius whole square, lithium ion radius whole square. They are approximately equal so that they will have similar atomic radius and similar electronegativity. So what are these anomalous properties and what are the diagonal relationship properties we will see now. Coming to some similarities between lithium and magnesium. Some similarities between lithium and magnesium. See, lithium ion Li plus. This Li plus ionic radius is what? 76 picometers. And Mg2 plus ionic radius is what? 72 picometers. So these are approximately same. That is due to diagonal relationship, right? And this lithium and magnesium directly combines with nitrogen to form their nitrides. But other elements of first group elements, beryllium, magnesium, other elements of first group elements, cesium, right, rubidium, potassium, they can't combine with nitrogen. But second group elements can combine with nitrogen directly on heating. But except lithium, other first group metals cannot combine with nitrogen directly. So it is the diagonal relationship with magnesium, that is anomalous property. So like this, lithium chloride and magnesium chloride. Lithium chloride and magnesium chloride, due to polarization, they are covalent in nature. Generally, metal, non-metal compounds are what? Ionic compounds. But due to polarization, lithium chloride and magnesium chloride are predominantly covalent in nature. They are covalent compounds. So as they are covalent compounds, they are soluble in organic solvents. They are soluble in organic solvents like ethanol, alcohol, ethyl alcohol. So if it is ionic compound, generally ionic compounds are soluble in water, right? But covalent compounds generally more soluble in organic solvents. So due to polarization, this LiCl and MgCl2 has covalent character. The other salts of first group are ionic. Potassium chloride, sodium chloride, rubidium chloride, they are ionic. But lithium chloride is covalent. So that's why these two compounds are soluble in ethanol. And another point is they are deliquescent. So when we take these salts in water, they absorb water and they form aqueous solutions. In their aqueous solutions, they exist as hydrated salt. So they form hydrated salts aqueous solution. This property is called deliquescence. So lithium chloride exists as LiCl2H2O and magnesium chloride exists as MgCl2 6H2O in its aqueous solution. But other salts of first group do not have deliquescence. Only lithium chloride has deliquescence and magnesium chloride has deliquescence. So lithium shows the diagonal relationship with magnesium. Next, coming to anomalous properties of aluminum or diagonal relationship with beryllium. As we discussed earlier, their polarizing power is same. Similar atomic radius are there for Be2 plus and Al3 plus. For Be2 plus and Al3 plus, they have similar atomic radius, similar electronegativity and same polarizing power. So other properties are this aluminum, beryllium, these two, both aluminum and beryllium not readily attacked by acids. They are not readily attacked by acids due to formation of oxide film on its surface. So beryllium are not attacked by acids because they form an oxide layer. Suppose this is beryllium aluminum. Some oxide layers are formed on its surface when they are treated with acids. For example, HNO3. Beryllium oxide layer is formed on its surface. It does not allow further reaction. If it is aluminum, when aluminum is treated with concentrated nitric acid, it does not allow aluminum to react further because aluminum oxide layer is formed on its surface. So some other examples I have given which forms passive oxide layer. You can see aluminum in the atmospheric oxygen is giving Al2O3. Al2O3 is passive oxide layer. Chromium Cr2O3 passive oxide layer. Titanium TiO2 passive oxide layer with air only. Beryllium in presence of air, it forms beryllium oxide. This beryllium oxide is a passive oxide layer. Now taking iron. So when iron is treated with concentrated HNO3, Fe3O4 is formed. Parasulfuric oxide, Fe3O4. This is also passive oxide layer. But here one question is, sir, aluminum does not get rust due to protective oxide film. This chromium, titanium, beryllium also not affected by acids or not affected by air or not affected by any other oxidizing agents at normal conditions because they form protective film. But iron will get rust. But you are saying that there is a passive oxide film. Means, so iron forms passive oxide film Fe3O4, but it is not stable. It is going to decompose. That's why iron gets corroded. Iron will get rust. But other elements are not getting rust due to formation of passive stable oxide films on their surface. Next, so when beryllium hydroxide with excess of NaOH, aluminum hydroxide with excess of NaOH. So they dissolve in excess of NaOH. They produces corresponding salts, that is berylate, BeOH4 2 minus is formed, and aluminum forms AlOH4 minus aluminate. Right. So beryllium, similar to aluminum, dissolves in excess of sodium hydroxide and they produces corresponding salts. But other elements of second group elements, they don't give these salts. They don't dissolve in excess of sodium hydroxide. That is an important point here. Now, here, take beryllium chloride and aluminum chloride. They are electron deficient. So they are incomplete octet. They have more tendency to accept the electron pair. So electron pair acceptors are called Lewis acids. Beryllium chloride, aluminum acids are good Lewis acids. That's why they are used as Friedel-Crafts catalyst. In Friedel-Crafts alkylation reactions, in Friedel-Crafts acylation reaction, we want Lewis acids. So these are the good Lewis acids. That is a similarity and anomalous property. Next, beryllium and aluminum ions have strong tendency to form complex. You can see beryllium with coordination number 4, Bf4 2 minus, aluminum with covalency 6 or 6 coordinate covalent bonds, AlF6 3 minus is formed. Next, coming to anomalous properties of boron. Anomalous properties of boron. First important thing is boron maximum covalency is 4, BOH4 minus or BF4 minus. Aluminum maximum covalency is 6. That is different from boron. AlH2O6 3 plus or AlF6 3 minus. So boron properties are, some properties of boron are different from aluminum. That is what? Boron maximum valence is 4, aluminum maximum valence is 6. So we discussed already. Due to absence of vacant orbitals in boron, it cannot extend its valency. That is one point. Now another point is, I am taking BF3 molecule. This is BF3 molecule. And I am taking ammonia here. In BF3, boron has vacant orbital, incomplete octet. Nitrogen has lone pair. So there is a day 2 bond formation. So with day 2 bond formation, here total valence is 4. BF3 valence is 3. After formation of this day 2 bond, maximum its valency becomes 4. Next, AlCl3 forms dimer. Its dimer is Al2Cl6. You can see this AlCl3 structure like this. This is one AlCl3. This is another AlCl3. This chlorine forms a day 2 bond with aluminum. This chlorine forms a day 2 bond with aluminum. There are 2 day 2 bonds in Al2Cl6. And if you consider this bond as bridged bond, these are bridged bond. 2 bonds are there. 2 bonds means 4 electrons and total 3 centers. These bridged bonds are 3 center 4 electron bonds. We have 3 center 4 electron bonds. This bond is what? 2 center 2 electron bond. In between aluminum chlorine, 2 electrons. 2 centers are there. This is 2 center 2 electron bond. This is 3 center 4 electron bond. Next, coming to another important point, I am taking BF3, BCl3, BBr3 and Bi3. So among all these halides of boron, Lewis acid character is more for Bi3. The least acidic nature is for BF3 because in BF3 molecule there is back bond. See, BF3 molecule has triangular planar structure, sp2 hybridization, and there is a vacant orbital. And fluorine has lone pair electron. To stabilize the boron, to give the complete octet, to give 8 electrons, the fluorine is contributing 2 electrons to the vacant orbital of boron. So that what happened? 6 plus 2, total 8 electrons. Which fluorine? The 3 fluorines are giving the lone pair of electrons. Maybe the first fluorine for some time, second fluorine for some time, third fluorine for some time. So all the 3 fluorine atoms are involved in the dative bond formation. Overall, always it will get 8 electrons, BF3 molecule. Right. So whenever this BF3 molecule approaches NH3 molecule, this back bond is going to break because it is relatively unstable. So this back bond is going to break and it will form a strong coordinate covalent bond with ammonia. Before that, it has back bond, but when it interacts with ammonia, that back bond is going to break and a strong new coordinate covalent bond is formed with other species. Right. So due to back bonding, BF3 has less tendency to accept the electron pairs from others. So why BCl3 has a less tendency from dative bond? Why there is no dative bond means distance. So this dative bond is almost like a pi bond. Already one sigma bond is there. So after formation of sigma bond, the next bond is what? Pi bond. So pi bond, how do you get pi bond? With the sidewise overlapping of p orbitals. So if I take chlorine, the distance between the boron and chlorine is large. So sidewise extent of sidewise overlapping is less. So chlorine has less tendency to form back bond. So it depends on other species. It will try to take electrons from the other species. That's why its acidic character is more. So as the size of the halogen increases, the tendency to form back bond decreases. So acidic nature increases. Now if I take elements of boron family, halogens of boron family, I mean BCl3, ElCl3, GaCl3, InCl3 and thalliumCl3 unstable. I am not writing this. Now here this is more acidic. BCl3 is more acidic. So I will give one important statement here. In 13th group elements, halides of boron family, acidic nature down the group decreases. The halides of boron family, boron to indium, acidic nature decreases. Boron is small in size, its electron activity is more, so it has more tendency to attract the electron pairs from others. But when I consider only boron halides with different halogens, but central atom is same, boron. In boron halides, more acidic character for Bi3, least acidic character for BF3. But in 13th group halides, BCl3 has higher acidic character, InCl3 has or TlCl3 has lowest acidic character. I hope you understood the difference. So these are the anomalous properties of boron from aluminum and other elements. Now coming to carbon. So here carbon, in case of carbon, in anomalous properties, first thing is it can't extend its valency, but silicon can extend its valency up to 6. But carbon cannot extend its valency more than 4. That is one point. Another point is due to its small atomic size, the carbon 2p orbitals involved in sidewise overlapping and gives pi bond. Carbon can form multiple bonds. It can form triple bond, it can form pi bond, it can form only sigma bond also. So carbon can form multiple bonds. Now another point is if I take silicon. Silicon has 3p orbital. So silicon with silicon, it can form sigma bond, but pi bond cannot be formed. I mean 3p orbitals cannot participate in sidewise overlapping. They can involve in direct overlapping, but sidewise overlapping is not possible. But if you take the same silicon with oxygen, pi bond is possible. Silicon is giving 3p orbital, oxygen is giving 2p orbital, 2p is smaller and 3p is bigger, but somehow it can form a pi bond. That pi bond is weaker than 2p pi bond. 2p pi bond is stronger than 3p and 3p is not possible. So what I am trying to say, carbon can form pi bond. Silicon can form pi bond with second period elements, but silicon cannot form pi bond with third period elements. 3p or 4p is not possible. That is one important point. And another important point is catenation. Catenation. The self-linkage of atoms to form very long chain is catenation. So carbon has the highest catenation property among all elements. So this catenation property depends on single bond strength. Carbon-carbon bond strength is very high compared to all other elements except hydrogen. So hydrogen single bond strength is very high compared to others, but hydrogen valence is one only. It can't extend it the chain. So after hydrogen, the highest bond strength is carbon. So that is 348 kilojoules per mole. So among all elements, the highest catenation property for carbon. In 14 group elements, after carbon, silicon, and after silicon, germanium, after germanium, tin. So the catenation tendency highest is for carbon, next silicon, next germanium, next tin. So once again, catenation is what? The self-linkage of atoms to form a long carbon chain is catenation. And catenation depends on the single bond strength, which has a higher single bond strength with multivalency, that is carbon. Next, coming to p pi d pi bonds. See, p pi d pi bonds means p orbital d orbital overlapping, sidewise overlapping gives p pi d pi bonds. So second period elements always gives p pi only. Second period elements always gives p pi only. When second period and third period elements combine, they can form p pi d pi bonds. Second period and third period elements with sidewise overlapping, they will give p pi d pi bonds. So in carbon dioxide, two pi bonds are there. Both are p pi bonds only. I have given some examples here. Carbonate. So this is carbon dioxide, two pi bonds. Both are p pi. Carbonate, C double bond O minus, and here O minus. One pi bond is there. So this is second period element, this is second period element, that is p pi only. NO3 minus. This is a NO3 minus structure. There is only one pi bond. That pi bond is p pi only. Nitrogen is second period, oxygen is second period element. Sulfur dioxide. Two pi bonds are there. Out of two, one is p pi bond, another one is p pi d pi bond. So other sulfate, phosphate, chlorate, XeO3, all examples are given. I will explain one example how to find the number of p pi d pi bonds. Let us take sulfur dioxide. To understand how to find the number of p pi d pi bonds. Here sulfur valence is 4. Sulfur ground state is 3s2, 3p4. In 3p4, 3s is completely filled. In 3p4, only one unpaired electron is 3s2, 3p4. The sulfur has two unpaired electrons. With two unpaired electrons, this SO2 can form only 2 bonds. But in SO2 total, how many bonds are there? 4 bonds. So to get valency 4, go to excited state. In excited state, it is 3s2, 3p3 and 3d1. 3d orbital is completely vacant. One of the p electron enters into 3d orbital. Now you see here, in 3s, 2 electrons. In 3p, 3 electrons, 3 unpaired electrons, and d, 1 unpaired electrons. Now 4 unpaired electrons are there. The sulfur is ready to form 4 bonds. So this is a shortcut to find p pi d pi bonds. Now let us assume this oxygen is going to bond with unpaired electrons. Oxygen valence is 2. Each oxygen can form 2 bonds. So here I am taking one oxygen. It will form a sigma bond. This is second oxygen. It is giving the sigma bond. And first oxygen, another bond is what? Pi bond. So this pi bond is formed with p orbital only. From oxygen, p orbital. From sulfur also p orbital. The first pi bond is formed by p orbital of oxygen and p orbital of sulfur. And the second pi bond is formed by d orbital of sulfur and p orbital of oxygen. So one bond is p pi and one bond is p pi d pi. This is how we are finding the number of p pi d pi bonds. So you can apply this concept for other examples also. Next, coming to anomalous properties of nitrogen. So regarding p pi d pi bonds, p pi bonds, valencies already we discussed. Here the new point is in the anomalous properties of nitrogen. The new point is, see this R3PO. They are given R3P double bond O, R3P double bond CH2, and PC2H5 thrice, and AsC6H5 thrice. In R3P double bond O, phosphorus valency is 5. Already 3 bonds with alkyl groups, 2 bonds with oxygen, phosphorus valency is 5. And what is this pi bond? This phosphorus is giving d orbital, oxygen is giving p orbital. So this is d pi b pi bond. In R3P double bond CS2 also, phosphorus is giving d orbital, carbon is giving p orbital. This is also d pi p pi bond. Nitrogen forms only p pi bonds, but phosphorus can form p pi d pi bonds. Next, another example. To understand this, I will give an example, that is, take metal carbonyls. Metal carbonyls. So this is a metal atom and this is ligand. Ligand has filled orbital. It has given this electron pair to vacant orbital of ligand. One sigma bond is formed. In case of metal carbonyls, the metal has one filled orbital and ligand has vacant orbital. Now there is a sidewise overlapping between the filled orbital of metal and vacant orbital of ligand. So here pi bond is formed. That pi bond is called back bond or synergic bond. Here how a synergic bond or pi bond, special pi bond, is formed between metal and carbonyl ligands. In the similar way, if you consider this PC2H5 thrice as a ligand, AsC6H5 thrice as a ligand, when these ligands combines with a metal, a dative bond is formed along with the sigma bond. So that dative bond is pi bond here. So here metal is giving the d orbital and the ligand electron pair is also coming from the d orbital. So this is d pi bond. Here this electron pair is coming from the d orbital and metal is also giving the d orbital. So the bond formed with these complexes is d pi. So what we are trying to say in this, phosphorus always form p pi. Sorry, nitrogen always form p pi. Phosphorus forms p pi d pi as well as d pi. These are the examples. Next, oxygen maximum covalency as per the NCERT is 4. Already we discussed it. So there is no extra points here. Now coming to fluorine. Here fluorine has a highest electronegativity and second highest electron gain enthalpy, and it is very unstable because bond dissociation enthalpy is less compared to bromine and chlorine due to lone pair repulsion. These points already we covered. Now among all halogens, fluorine, chlorine, bromine, iodine, these forms oxoacids. But fluorine cannot form oxoacid. But one exceptional oxoacid they observed, that is HOF. Like HClO, hypochlorous acid, here one oxoacid was observed. In JD it was clearly mentioned as this fluorine oxidation state is -1. Remember, it is not +1, it is -1. But HClO, chlorine oxidation state is +1. In the oxoacids of halogens, halogen shows positive oxidation state. But in HOF, fluorine does not have positive oxidation state, it is -1 only. Accordingly, oxygen +2 and hydrogen is +1. So JD it is mentioned that, I will show this, fluorine oxidation state is -1 only, right? And fluorine is highly reactive. All fluorine reactions are highly exothermic. They are highly exothermic in nature. Next, coming to uses. So you can read all these uses. Just pause your video and read those uses. All elements uses I have written here. Boron uses, aluminum uses, carbon uses, nitrogen uses, and oxygen uses, chlorine and noble gases. Noble gases uses are very important. Many times they ask questions. Now, chlorine uses one important point. It's a bleaching agent. It is a bleaching agent. Chlorine is bleaching agent. Moist chlorine is a bleaching agent, right? So this bleaching agent topic we'll study later. Now this chlorine is used in the extraction of gold and platinum. How it is used in the extraction of gold and platinum, I'll show. That is in the form of aqua regia. So aqua regia is 3 parts of HCl and 1 part of nitric acid. This mixture is aqua regia. When HCl and HNO3 are combined in the 3:1 ratio, it produces nitrosyl chloride. This nitrosyl chloride is unstable, therefore it decomposes to form nitric oxide and nascent chlorine. This nascent chlorine is highly reactive. This nascent chlorine reacts with the gold and produces auric chloride, and further it reacts with the HCl and produces chloroauric acid, HAuCl4. This is how it is extracting the gold in the form of HAuCl4. After that, we are able to decompose that. Next, how platinum is extracted. How platinum is extracted? So we know that this chlorine, nascent chlorine is formed. It combines with platinum. Any other acid, HCl does not react with platinum. Nitric acid does not react with platinum. Only aqua regia reacts with platinum because there is a formation of nascent chlorine. Now, this platinum reacts with chlorine and produces PtCl4, and PtCl4 further reacts with HCl and produces H2P2Cl6. This complex is formed, right? Hexachloroplatinic acid. This is how the chlorine is used to extract the gold and platinum in the form of aqua regia. And some important things are chlorine, phosgen. For the preparation of phosgen, COCl2, tear gas, chloropicrin is a tear gas, CCl3NO2, and mustard gas formula is given in NCERT. You should read it. This is mustard gas formula, right? And noble gases. All elements uses once pass this video and read those applications. So they are important. We can expect questions from this area also. Now, chemical reactivity, oxides and oxoacids. First, let us discuss chemical reactivity. So here all boron families, carbon families, nitrogen families, all 13 to 18 groups, chemical reactions we will discuss. Next we'll go to oxides and oxoacids. First, I'm coming to reactivity towards oxygen, reactivity towards air or oxygen. The boron family. So boron family forms M2O3 type of oxides. M2O3 type of oxides. Boron, aluminium, gallium, and other. Thallium, Tl2O3 is not stable. So it is stable with Tl2O. +1 oxidation state is stable for thallium. We know that. Tl2O3, thallium oxidation state is +3. That is unstable. Right. So here some important points are boron in crystalline form unreactive. Boron has different forms. Amorphous form is there, crystalline form is there. So here crystalline forms are not reactive, but amorphous form can react with air, react with oxygen. Suppose when the boron is heated with air at particular temperature, it reacts with oxygen, it combines with oxygen and produces B2O3 oxides and produces boron nitride. Other elements also gives oxides and then nitrides when they are heated in the air. But crystalline boron does not react. Now coming to carbon family. So when carbon family reacts with oxygen, they form two types of oxides, MO and MO2 types of oxides. For example, carbon CO and CO2 type of oxide. So even silicon gives silicon dioxide and silicon monoxide also, but silicon monoxide exists only at high temperature. As coming to nitrogen family, nitrogen common valence, nitrogen family common valency common oxidation state is +3, and higher oxidation state is +5. So it will give E2O3 and E2O5 types of oxides when they are heated with oxygen. Oxygen family, they give EO2 and EO3 types of oxide. For example, if I take sulfur, SO2 and SO3 type of oxides. So oxygen is not giving any oxide because for oxides we want oxygen. Oxygen exists in two forms, O2 and ozone, oxygen and ozone. Here, the sulfur, selenium, tellurium, polonium, all these elements gives EO2 and EO3 types of oxides. Now, O3 is ozone, SO2 gases, TO2 is solid, TO2 is solid. Now, in this SO2, SeO2, TeO2, SO2 reducing nature is more than SeO2 and SeO2 reducing nature is more than TeO2. Simple example. So, why SO2 has more reducing nature? I am taking SO2. Here, sulfur oxidation state is +4. But sulfur stable oxidation state is what? SO3, +6. So sulfur has tendency to go from +4 to +6 oxidation state. So it is going for oxidation, which undergoes oxidation acts as reducing agent. And tellurium has more tendency to be in the lower oxidation state. So TeO2 is an oxidizing agent. But sulfur wanted to be in the higher oxidation state, so it is reducing agent. I hope it is clear. So reducing nature of SO2 is greater than selenium dioxide, and that is greater than tellurium dioxide. Next, when it comes to halogen family, when they are heated with oxygen, right? So fluorine gives two compounds, OF2 and O2F2. We don't call OF2 and O2F2 as oxides. We used to call fluorides, because the name of the compound is based on the electronegativity. Fluorine is higher electronegativity. It is better to call fluorides. The oxygen difluoride and oxygen monofluoride. In these two compounds, OF2 is thermally stable. OF2 is thermally stable at room temperature 25 degrees Celsius, means O2F2 is relatively unstable. So this OF2 and O2 are fluorinating agents because they are ready to give fluorine. So OF2 and O2F2 can exist, but they are not stable. Easily they decomposes. They are ready to give fluorine atoms. That's why these are called fluorinating agent. And this property is used in the application to remove plutonium, to extract plutonium. So how to extract plutonium? So taking O2F2 with plutonium minerals. There will be so many impurities, but when this plutonium, impure plutonium, this is impure plutonium, when it is treated with O2F2, it produces PuF6. It reacts with only pure plutonium atoms, impurities are left. So when PuF6 is heated, it decomposes and it will give the pure plutonium. So this is how we are removing the plutonium from spent nuclear fuel by using the fluorinating property of O2F2, because this is unstable. Next, chlorine, bromine and iodine form oxides. So all halogens. So we discussed about binary compounds of fluorine with oxygen. Now next compounds are chlorine, bromine and iodine. They form oxides. They are oxides from +1 to +7. +1 is there, +3 is there, +5 is there, and +7 is also there. So here stability, generally this oxide stability or any compound stability based on kinetic factors and thermodynamic factors. Most of the cases we used to follow thermodynamic factors. Here, based on the kinetic and thermodynamic factors, the stability order of their oxides, iodine is greater than chlorine, chlorine is greater than bromine. So these iodine oxides are more stable because the polarizability between iodine and oxygen in their respective oxides is more. Iodine is large in size, oxygen is small in size, polarizability will be more, and better bonds are formed between iodine and oxygen. That's why iodine oxides are more stable. So remember, it is based on both kinetic and thermodynamic. Next, after iodine, chlorine oxides are more stable because chlorine can form strong covalent bonds. I mean strong multiple bonds. Compared to bromine and compared to iodine, due to small atomic size, chlorine can form stronger, relatively stronger covalent bonds. So in the last previous topics also we discussed that when the p orbital's distance is less, stronger pi bond is formed. When p orbital's distance is more, weak pi bond or no pi bond is formed. So due to small atomic size, compared to bromine and iodine, chlorine has smaller atomic size. It is giving 3p orbital. This 3p orbital combines with 2p orbital of oxygen, giving relatively stronger pi bond. But similar types of bonds cannot be observed in iodine and bromine. So higher oxides of halogens tend to be more stable. I mean, at higher oxidation state. So +7, +5 oxidation states. Oxides with +7 and +5 compounds are more stable compared to +1 and +3. So these statements are very important because they may ask as it is statement questions or assertion reason questions. Next, here in chlorine oxides, Cl2O, ClO2, Cl2O6, Cl2O7, these oxides are given in NCERT. They are strong oxidizing agents. They tend to explode. Strong oxidizing agent means there is fast reaction, so explosion takes place. Bromine oxides, Br2O, BrO2 and BrO3, they are least stable, right? They exist only at low temperatures and they are also powerful oxidizing state. So as they are less stable, they are powerful oxidizing agents. Next, iodine oxides are I2O4, I2O5, I2O7 given in the NCERT. These are water insoluble solids. They decompose on heating. Next, here from these halogens, in the halogen oxides, two important points. ClO2, chlorine dioxide. Chlorine dioxide is used as bleaching agent. This is used to remove the colors of paper pulp, textiles and water treatment. So bleaching means the process of removing natural color from the given substance, generally organic substance. From organic substance, removing the natural color by using certain agents. That phenomena is bleaching, and the chemicals used for bleaching are called bleaching agents. Right. Here ClO2 acts as bleaching agent only in acidic medium. In acidic medium, it changes the colored substance into colorless substance. If I take a neutral medium, so when ClO2 dissolved in water, it is giving HClO2 and HClO2. Doesn't act as bleaching agent. And ClO2 in alkaline medium does not act as bleaching agent. So ClO2 is a bleaching agent, and it can be used as bleaching agent in acidic medium only. Next, another most important point is I2O5, one of the important oxide of iodine, I2O5. This I2O5 is used to estimate carbon monoxide, for estimation of carbon monoxide. So how it is used in the estimation of carbon monoxide means when I2O5 is treated with CO, it produces CO2 and I2. And this I2 is treated with hypo. Now the reaction is I2 with Na2H2O3 gives sodium tetrathionate and sodium iodide. Now the gram equivalence of hypo used is equal to gram equivalence of CO. So by measuring the gram equivalence of hypo used in this titration is equal to gram equivalence of carbon monoxide. This is how we are estimating the carbon monoxide. Next, in oxides, another most important part is nature of oxides. Which oxides are acidic, which oxides are basic, and which oxides are amphoteric, and some oxides are neutral. Here, out of all oxides, CO, NO, N2O, these are neutral oxides. And basic oxides from boron family, acidic oxides from boron family, only B2O3. Next, from 14 group elements, carbon dioxide, silicon dioxide, germanium dioxide, silicon monoxide, right? These are all acidic. So N2O3, P2O3, NO2, N2O5, P2O5, I2O5. So from NCERT, by using the NCERT information, I have classified all these oxides into acidic, amphoteric, and basic. So follow this. So these are the amphoteric oxide: aluminium, gallium, tin with +2 and +4 oxidation state, arsenic, antimony oxides are amphoteric. Remember, here TeO2 is acidic, TeO3 is acidic. Generally, this tellurium is a metallic character is there. So metal oxides are basic oxides. But when oxidation state increases, Even in the metal oxides, acidic character increases. In D block elements, transition metals, you will see CrO3, chromium trioxide is acidic. But Cr2O3 is amphoteric. And chromium oxide, chromium monoxide is basic. So as the oxidation state increases, acidic character increases. Right? So because of that reason, TeO2 and TeO3 are acidic in nature. Right. Next, another important point from oxides is in SO3 and SO2, which has more acidic nature. Simple. Based on oxidation state, sulfur has +6, this sulfur has +4, +6 oxidation state is higher. So SO3 acidic character is more than SO2. In oxoacids also, H2SO4 sulfur is +6, H2SO3 sulfur is +4. So with +6 more acidic character. So sulfuric acid is more acidic than sulfurous acid. So this concept is followed for all other acids. Right. Now coming to, but there is an exception in oxoacids. One exception is there. Here H3PO2 is more acidic than H3PO3, and H3PO3 is more acidic than H3PO4. Here phosphorus oxidation state +1. This phosphorus is +5. Sorry, this phosphorus is +3 and this phosphorus is +5. So general concept is what? In oxides and oxoacids, acidic character increases with oxidation state. But in case of phosphorus oxoacids, it is not following that rule. It is not following that trick. So here H3PO2 is more acidic than H3PO3 and H3PO3 is more acidic than H3PO4. It is an exception. It depends on the number of hydrogen atoms. So this reason and this concept takes more time. That's why I'm not explaining. It is based on the number of hydrogens attached to the phosphorus or number of oxygens attached to the phosphorus. So other oxoacids, there is no any exception, only in the phosphorus oxoacids. Now another point is B2O3, Al2O3, which is more acidic. B2O3 is more acidic. How do you say? So boron electronegativity is more than aluminum. In HClO3, HBrO3, chloric acid and bromic acid, which is more acidic. So chloric acid is more acidic than bromic acid because the electronegativity of chlorine is greater than bromine. So when the electronegativity of the central atom is more, acidic nature is more, or oxidation state increases, acidic nature is more. Next, so reaction towards oxygen is completed. Now reaction towards halogens. First coming to boron family. So boron gives EX3 type of compounds. Fluorine, chlorine, bromine, iodine all will form except TlI3 because thallium +3 oxidation state not stable. Now one NCERT question is anhydrous aluminum chloride has white fumes around the bottle, around itself, white fumes. What is the reason? When anhydrous aluminum chloride is exposed to the atmosphere, it dissolves in water and produces aluminum hydroxide and HCl gas. Right? So this HCl gas, the dense, large quantity of HCl gas around aluminum hydroxide gives the turbidity, white fumes appearance. That is due to formation of HCl. Yes, coming to carbon family. Carbon family, basically it forms two types of halides, MX2 and MX4 types of halides. With +2 oxidation state MX2, with +4 oxidation state MX4. Right, but carbon only +4, carbon with halogens +2 is not there, only +4 is there. Right, now here some important points are there. In tetrahalides, all halides are covalent. Only SNF4 and PBF4 are ionic. Remaining all tetrahalides are covalent. Right? So down the group, the atomic size increases, metallic character increases, so ionic character is also increases. That's why, and fluorine is small atom. Right? So generally ionic covalent, how do you distinguish? Based on the sizes. If the compound is like this is ionic. Fajans rule. If the compound is like this is covalent. Cationic size is more, ionic. Anionic size is more, covalent. Almost equal sizes are there. So both ionic character and covalent character. So based on that, you can understand SNF4 and PBF4 has more ionic character. They will come to this category. Other halides, they are covalent. PbI4 does not exist. Inert pair effect. Lead plus 4 is not stable. Plus 2 is stable. Another important point that NCERT explanation is for PbI4. So I want to get PbI4. So lead is fourth group element. Its outer configuration is NS2, NP2. NS is completely filled. NP, 2 electrons are there. 1 vacant orbital is there. So now what happened here? With this electron, iodine forms one bond. With this electrons, iodine is making another bond. So 2 sigma bonds are formed. In the formation of 2 sigma PbI bonds, some energy is released. That energy is not sufficient to excite this NS electrons. Right. In case of CCl4, after formation of 2 sigma CCl bonds, the NS electron of carbon is excited to NP orbital. Then another bond is formed. So carbon-chlorine bond enthalpy is sufficient enough to excite the NS electrons of carbon. But lead and iodine bond enthalpy is not sufficient enough to excite the NS electrons of lead. So that is the reason why PbI4 does not form. Right? In simple words, inert pair effect is also, but this is NCERT explanation for that. Now, in all tetrahalides except CCl4, remaining all halides are going to hydrolyze. So if you see the hydrolysis of silicon tetrachloride, you will understand why CCl4 does not go for hydrolysis. See SiCl4 and H2O. Silicon has vacant orbital. Is water like a nucleophile, or this lone pair oxygen attacks the silicon and produces H4SiO4 or SiOH4, which is called silicic acid, and HCl is formed. So this hydrolysis reaction is taking place due to presence of vacant orbital of silicon and lone pair of water. When we take CCl4 with water, water has lone pair in the oxygen, but carbon does not have vacant orbital. It is not able to attack the carbon, so hydrolysis does not take place. Except CCl4, all other 14th group element halogens undergoes hydrolysis because they have vacant orbitals. Next, coming to nitrogen family. So with plus 3 and plus 5 oxygen state, EX3, EX5 halides are there. And covalent nature increases with oxidation state. Covalent nature is directly proportional to oxidation state, because when the positive oxidation state increases, the size decreases. Anion size will be larger than cation size, because when cation or positive oxygen state increases, its size decreases and it develops covalent character, that is polarization or Fazan's rule. Right? Among all trihalides, NF3 is only known. NF3 is only stable. All others are unstable. This NF3 also exists in red liquid. NF3 is a red liquid and it is explosive. It is very unstable. Other trihalides do not exist. It is existing but unstable and it is explosive. Now, trihalides, all trihalides are covalent except BiF3. BiF3 is ionic. Bismuth is large compared to others. Fluorine is small, so it is ionic. Other trihalides are covalent. Right. Oxygen family. So, how they react with halogens and what are the compounds? So these chalcogens or oxygen family members gives EX6, EX4, EX2, EX type of halides. Hexahalides, tetrahalides, dihalides and monohalides are formed. Hexahalides, EX6, they have octahedral geometry. EX4, for example, SF4, it will have seesaw geometry. And EX2 bend shape. EX2 bend shape. And E2X2 geometry is open book structure. E2X2 open book structure like hydrogen peroxide. Hydrogen peroxide structure is open book structure. So the structure will be like this. This is open structure. So this oxen family members are giving hexahalides, tetrahalides, dihalides, and monohalides. The stability of halides increasing with electronegativity. So fluorine with fluorine is greater than chlorine, next bromine, and next iodine. So among all hexahalides, only hexafluorides are stable. Hexafluorides are stable. So SF6 is stable, SeF6 is stable, TeF6 is stable. I mean, when sulfur combines with chlorine, selenium combines with chlorine, or tellurium combines with chlorine or bromine, those compounds are relatively unstable, but with fluorine they are stable. Next, SF6 is exceptionally stable because of steric reasons. So, for example, this is sulfur. This is sulfur. So, around sulfur atom, 6 fluorine atoms are there. This is first fluorine, second, third, fourth, fifth, sixth. Now, if I take chlorine, the chlorine atom is large. So, 6 chlorine atoms or 6 bromine atoms or 6 iodine atoms around the sulfur atom, so steric repulsions are there. So, due to repulsions, that is not stable. But fluorine is smaller. 6 fluorine atoms can accommodate on the surface of the sulfur. So, that is stable. Because of less steric repulsions, SF6 is more stable. Others are unstable among all hexafluorides. Next, here in all hexafluorides are gases. SF6 is a gas and SF4 is a gas, SeF4 is liquid and TeF4 is a solid. Now some examples of halides given here. Monohalides E2X2, EX exists as dimer E2X2, S2F2, S2Cl2, S2Br2, Se2Cl2, Se2Br2. And EX2 type of halides are all elements except oxygen form dichlorides and dibromides. Except oxygen, all are giving dichlorides and dibromides. And EX4 halides are SF4, SeF4 and TeF4. Here one important point is this SeCl2, I mean EX2 type of halides undergoes disproportionation. So this SeCl2 undergoes disproportionation is giving SeCl4 and selenium. So here the selenium oxidation state is +2, this selenium is +4 and this is 0. So +2 to +4 oxidation and +2 to 0 reduction. So same element undergoes both oxidation and reduction, hence it is a disproportionation reaction. Now coming to halogen family, chemical reactivity towards halogens. Halogens with halogens, they are called interhalogens. Halogens with halogens, they are interhalogens. Now here you can see one tabular form on the screen, but this complete data is not required. Physical state and colors not required, but the hybridization and geometry is enough, right? So we have 4 types of interhalogens, 4 types of interhalogens. Here X-1, I will write it as AX, AX3, AX5 and AX7. 4 different types of interhalogens are there. Halogens with halogens, interhalogens. Right. Here A is a halogen, X is also halogen. So A is less electronegative halogen. Less electronegative halogen. And X is what? High electronegative halogen. High electronegative halogen is X. Less electronegative halogen is A. Right. For example, CLF. In CLF, fluorine is high electronegative, chlorine is less electronegative. Or take ICl3, chlorine is less electronegative, more electronegative, iodine is less electronegative. So A place will have less electronegative halogen and X place we will have higher electronegative halogen. So there are 4 types of interhalogens: AX, AX3, AX5, AX7. These interhalogens are highly reactive. Means the compounds are formed, interhalogens are formed, but they are not very stable. They are not stable. So their reactivity is more. So these interhalogens reactivity is more than halogens. So the bond between chlorine, chlorine, bromine, bromine, iodine, iodine is stronger than interhalogen bonds between chlorine and fluorine, between bromine and fluorine, like that. So interhalogens reactivity is more than halogens. Here exception is what? Fluorine. Fluorine bond dissociation enthalpy is less, fluorine reactivity is more. So fluorine is more reactive than interhalogens, and interhalogens are more reactive than normal halogens, right? So if we come to geometry, AX type of solids, AX type of solids geometry is linear. All these are linear molecules. And AX3 type, T shape, ClF3, BrF3, IF3, T shape. And AX5 square pyramidal geometry. And AX7 is pentagonal bipyramidal. So here hybridization, lone pairs geometry is important in case of these interhalogens. Next, coming to hydrides. So reaction towards hydrogen. When an element combines with hydrogen, the binary compound formed is called hydride. Now, nitrogen family hydrides, oxygen family hydrides, and halogen family hydrides, some similarities are there. So if you understand the concept of one particular type of hydrides, the same concepts will be repeated for others. Now, bond dissociation enthalpy. So let us discuss all these points one by one. So bond dissociation enthalpy. Take ammonia and phosphine. In ammonia, we have NH bond, and phosphine pH bond is there. Here electronegativity difference increases, bond strength increases. Nitrogen hydrogen electronegativity difference is more, bond strength is more. So the bond dissociation enthalpy of NH3 is greater than pH3. So in the 15th group hydrides, down the group, electronegativity gradually decreases. So bond dissociation enthalpy gradually decreases. So ammonia to bismuthine gradually decreases. See, ammonia is non-poisonous. Remaining all phosphine, arsine, stibine, bismuthine, these are all poisonous gases. That's why nitrogen family elements are called nicogens. Now acidic nature. So when bond dissociation enthalpy is less, easily it releases hydrogen. For example, BaH3 is there. In BaH3, bond dissociation enthalpy is very less. Easily it is releasing the hydrogen. So bismuthine acidic nature is more. Bismuthine acidic nature is more than stibine. Stibine is more than arsine. Next phosphine. And the least acidic nature is ammonia, because its bond dissociation enthalpy is more. And reducing nature. Reducing nature means what? Reducing acid means which undergoes oxidation. One of the definition of oxidation is what? Loss of hydrogen atoms. Loss of hydrogen atoms. So the hydride which has less bond dissociation enthalpy easily loses hydrogen and easily undergoes oxidation. It acts as a better reducing agent. So bismuthine is a good reducing agent compared to others. Bismuthine is good reducing agent. Next, basic nature. Here basic nature, these are our Lewis bases. Ammonia, phosphine, arsine, stibine, bismuthine, these are all Lewis bases. Now I am taking ammonia here. See, nitrogen is more electronegative and nitrogen is carrying one lone pair. So this more electronegative nitrogen is attracting the electron pair towards itself. So this is the bond moment, dipole moment. So from the three nitrogen-hydrogen bonds, the bond moment is towards the nitrogen atom. So nitrogen gets more electron density. So when nitrogen has higher electron density, it will have more tendency to release the electron density. But compared to other hydrides, electron density at the central atom is less. Once again, so I am taking nitrogen compound, nitrogen hydride, ammonia. In ammonia, 3 NH bonds are there, right? Nitrogen is attracting the shared pair of electrons towards itself. Already nitrogen has lone pair. Now 3 bond pairs are coming towards the nitrogen. So high electron density is accumulated at the nitrogen. So nitrogen compound acts as good Lewis base. So As the electronegativity of the central atom decreases, the basic nature gradually decreases. Now dipole moment. Dipole moment depends on the electronegativity difference. We know that nitrogen has higher electronegativity, so the bond pair movement towards nitrogen is more compared to others. So this is the order of dipole moment. And boiling point. Boiling point depends on intermolecular forces. Boiling point depends on intermolecular forces. So intermolecular forces means dipole forces, right? Dipole induced dipole forces, induced dipole forces. So these are intermolecular forces. These intermolecular forces increases with the molecular weight. Intermolecular forces directly proportional to molecular weight. Therefore, we expect the increase in intermolecular forces, the increase in boiling point in the hydrides. In addition to these dipole interactions, in ammonia, hydrogen bonding is hydrogen bonding. Which hydrogen bonding it is? Intermolecular hydrogen bond. Between ammonia molecules, hydrogen bonding is formed. So it has greater attraction forces compared to few hydrides. Now, once again, here boiling point depends on intermolecular forces. In case of hydrides, the intermolecular forces are dipole intermolecular forces. Right. Now, in addition to these dipole interactions increases with the molecular weight. So in hydrides down the group, intermolecular forces increases. So bismuthine should have higher boiling point. So there is higher boiling point. Next is stibine. So here third position ammonia is coming, that is due to hydrogen bonding. In ammonia, in addition to the dipole interactions, there is intermolecular hydrogen bonding. Because of this intermolecular hydrogen bonding, ammonia boiling point is greater than arsine and phosphine. Next, melting point. Melting point depends on its crystalline structure. It depends on intermolecular forces, depends on its packing or crystalline structure in its solid state. Right. So ammonia is greater than stibine is greater than arsine is greater than phosphine. Next, the very important point is the standard heat of formation of ammonia is negative. Among all hydrides, the standard heat of formation of ammonia is negative. All others are positive value. Heat of formation of ammonia is negative. All others are positive. This is very important. Now, the same concept. Next, coming to bond angle here. Coming to bond angle. Coming to bond angle. See, in general or as per the values, ammonia bond angle is greater than phosphine is greater than arsine is greater than stibine is greater than bismuthine. So down the group, bond angle decreases. First, I will tell you why bond angle decreases. Take ammonia, this is NH3. Next, phosphine, this is phosphine, PH3, right? Now, all the three bond pairs are moving towards the nitrogen in ammonia. As the bond pairs are moving close to the nitrogen, the distance between the bond pairs decreases, bond pair repulsions increases, so bond angle increases. But phosphorus electronegativity is less, the bond pair movement is less, the change in boiling point is also less. So ammonia bond angle is greater than phosphine. This is the general concept. Next, another important point in case of bond angles of 15 group elements, if you see their values, see here ammonia 107.8, phosphine 93.6 degrees, arsine 91.8, stibine 91.3, and bismuthine 90.5. From phosphine to bismuthine, the bond angles are almost 90 degrees. Almost 90 degrees. Ammonia is 107, right? Tetrahedral geometry expected, but there is one lone pair, so pyramidal shape, 107 degrees. But phosphine to bismuthine, their bond angles are almost 90 degrees. The reason is in phosphine, arsine, stibine, and bismuthine, due to the large atomic size of their central atom. What are the central atoms? Phosphorus is central atom in PS3, arsenic is central atom in ASH3, antimony is central atom in SPS3, bismuth is central atom in bismuthine. So all these central atoms are large in size. The energy difference between s orbital and their p orbitals is more, so they cannot participate in hybridization. They can't involve in hybridization. So hybridization means what? The intermixing of atomic orbitals of almost same energy to give same number of new identical orbitals, which are called hybrid orbitals. That phenomena is hybridization. So here what I am trying to say, hybridization is completely, it's a concept of central atom. So the atomic orbitals, some atomic orbitals involves in intermixing, right? That intermixing phenomena is hybridization. In case of phosphine, arsenate, stibine, and bismuthine, s orbitals, p orbitals energy difference is more. They can't involve in hybridization. So hybridization is not applicable for them. So in the formation of these hydrides, pure p orbitals are involved. You can see on the screen, pure p orbitals are involved. Ammonia, sp3 hybrid orbitals are involved in the formation, but phosphine, arsine, stibine, bismuthine, pure p orbitals are involved. So whenever pure p orbital or s orbitals are involved, that concept is valence bond theory. According to valence bond theory, the bond angle is 90 degrees. So that is a reason why these compounds bond angles are close to 90 degrees. Why not close to 107 degrees? Means the reason is due to large energy difference between s orbital and p orbital, they are unable to involve in hybridization. So here pure p orbitals are involved in the formation. So VBT concept is applicable. According to VBT, any molecule bond angle is what? 90 degrees when p orbital is involved. Right. Now coming to oxygen family, concepts are same as 15th group. Bond dissociation enthalpy depends on electronegativity difference. So in water, oxygen hydrogen electronegativity difference is more. So bond dissociation enthalpy is more. H2TE bond dissociation enthalpy is less. So easily it gives hydrogen. So its acidic nature is more, gradually decreases. Next, reducing nature means which loses hydrogen readily. H2TE is readily losing hydrogen, readily undergoing oxidation. So because its bond dissociation enthalpy is less. So bond angle is directly proportional to electronegativity of central atom. Bond angle is directly proportional to electronegativity of central atom. Then water has high bond angle, gradually decreases. Dipole moment is directly proportional to electronegativity difference between central atom and bonded atom. So water has high dipole moment. Next, boiling point. Boiling point is directly proportional to intermolecular forces and molecular weight. So molecular weight wise, H2TE has highest molecular weight. It has relatively higher boiling point. But in case of water, due to intermolecular hydrogen bonding, water has highest boiling point among all hydrates. After that, reverse order H2TE due to highest molecular weight. Melting point depends on its crystalline structure in its solid state. So water has more melting point. Next, H2TE, H2SE, and least melting point is H2S. And this is very, very important. Standard heat of formation of water and standard heat of formation of H2S are negative. Previously, in the 15th group hydrides, standard heat of formation of ammonia is negative, all others are positive. Here, water formation and H2S formation are negative, remaining all are positive. So generally, what we will discuss now, standard heat of formation negative means the ease of formation is more, stability is more. If some compounds, its standard heat of formation is positive means the ease of formation is less or it is unstable. So the negative heat of formation is directly proportional to stability and directly proportional to ease of formation. Next, coming to halogen family, simple bond dissociation enthalpy of HF is greater, electronegativity difference is more. HI, bond dissociation enthalpy of HI is less, that's why it is more acidic. You know that HI, HBr, HCl, these are strong acids. Because their bond dissociation enthalpy is less, easily they will give hydrogen. They are strong acids. But what about HF? HF is a weak acid. Bond dissociation enthalpy is more. Bond dissociation enthalpy is more. It can't give hydrogen readily. So HF is a weak acid. These are strong acids. Next, HI is a strong reducing agent. Even in organic chemistry, we are using hydrogen iodide. So strong reducing agent because easily it produces hydrogen. Dipole moment directly proportional to electronegativity difference. Boiling point directly proportional to boiling point. HF is greater than HI. HI is greater than HCl. HI is greater than HBr. HF is greater than HI. HI is greater than HBr. HBr is greater than HCl. This is the order of boiling point. Why HF has high boiling point means intermolecular hydrogen bonding. In other molecules, which factor is to be followed? Dipole-dipole interactions and molecular weight. So melting point HF is greater than HCl, HBr, HI. This is about hydrides. So if you understand one hydrides logic, remaining all are same and easy. Next, other reactions. Now we discussed reactivity towards oxygen, reactivity towards halogens, and reactivity towards hydrogen, hydrides, halides, and oxides. Now, reaction with metals or some other rare reactions. So, boron does not react with acids and alkalis even at moderate temperature because boron has a strong crystalline polyhedral structure. Icosahedral units are there. Easily, it won't react with acids and alkalis. But aluminum reacts with acid. Aluminum reacts with base also, right? Here, aluminum is reacting with HCl, and this aluminum is reacting with the sodium hydroxide. So these are the corresponding products. And concentrated nitric acid renders aluminum passive. This one already we have seen. So aluminum, beryllium, and chromium, titanium, iron forms passive oxide layer when they expose it to oxygen. But iron forms passive oxide layer Fe3O4, but Fe3O4 is not stable, it decomposes and it will get rust. But others, aluminum, beryllium, boron, right, titanium, they form oxide layer on its surface when they expose it to the atmosphere. So that oxide layer does not allow further reaction, right? That is called passivity or passive oxide layer formation. Similar to that, when aluminum is exposed to concentrated nitric acid, immediately it forms oxide layer on its surface. Once that oxide layer is formed, it does not allow further reaction. You can see this is the protective oxide layer. Next, 15 group elements combines with metals. They produces calcium nitrates, Ca3N2, calcium phosphide, sodium arsenide, zinc stibnite, and magnesium bismuthide. And halogens also reacts with metals to form MF, MCl, MBr, Mi. Now, here coming to noble gases. Noble gases, the first noble gas compound is what? Xenon platinic fluoride. Here we have some exceptions. Xenon platinic fluoride. In this, xenon oxidation state is +1. Xe plus Pt Xe plus Pt F6 minus. Xe plus Pt F6 minus. So this is exceptional oxidation state for xenon. Xenon +2 is there, +4 is there, +6 is there, +8 is there. And the only compound in which xenon has +1 oxidation state is xenon platinum fluoride, and this is the first noble gas compound. So here +1 oxidation state. In PTF6, let us take platinum oxidation state is X and fluorine is 6 into -1 is equal to -1. Then X is equal to what? X is equal to +5. So generally platinum oxidation state +2 and +4, but here platinum oxidation state is what? +5, right? So this is one exception. It's a first noble gas compound and xenon oxidation state is +1 here, platinum oxidation state is +5 here. Now, previously inert gases, these 18 group elements are called inert gases. They are inert in nature, they are less reactive, they don't form compounds. But later the name changed as noble gases. So why they changed inert gases to noble gases means each and every element in the periodic table trying to get this 18 group elements configuration, octet configuration or duplet configuration. So everyone is following the 18 group elements. For everyone, role model is 18 group elements. So that's why they are called noble gases. So they may call inert gases or noble gases, right? Initially, they did not find any compounds, but later many compounds of xenon and krypton also we have seen. For krypton, one compound they observed, KrF2. For xenon, many compounds, xenon fluorides, xenon oxides, xenon oxyfluorides, many compounds are there, right? So how this particular compound is discovered, I will explain shortly. So previously, we don't have any inert gas compound. So many people tried and failed. But one scientist, when he was doing experiment with complex compounds, he observed O2PTF6, oxyplatinum fluoride complex. Here also oxygen is O2 plus. O2 plus means oxygen oxidation state is plus of. Oxygen oxidation state is plus of. This is also exceptional oxidation state. Anyway, coming to the topic. Oxyplatinum fluoride, he observed that this oxygen ionization enthalpy is what? 1175 kilojoules per mole. So if we compare this ionization enthalpy with xenon ionization enthalpy, oxygen is 1175, xenon is 1170. So with higher ionization enthalpy, when oxygen is giving a complex compound, why not xenon? He thought that why don't xenon gives compound? Oxygen is giving, both are having same ionization enthalpies. Oxygen compounds are there, but why there is no xenon compound? He started doing some research on the xenon and succeeded with the formation of a new compound, xenon platinic fluoride. So once the xenon platinic fluoride is formed, so many compounds were prepared and identified, right? So till now, xenon has oxides, fluorides, oxyfluorides, and krypton KrF2, whose oxidation state is +2. Now, xenon fluorine compounds are, so these are the preparation, XCF2 preparation, XCF4 preparation, XCF6, and their conditions. So important, the temperature, pressure, and the composition, everything is important. You can pause this video and read those reactions. And xenon oxygen compounds are coming with partial hydrolysis of XCF6, with partial hydrolysis one product, with complete hydrolysis another product. So here you will get xenon oxides and xenon oxyfluorides. So some of the reactions are disproportionation reactions. So that point is important. Which of the following reaction is disproportionation, which is not disproportionation? So this disproportionation reaction topic we'll see again. Next, xenon fluorides. These xenon fluorides are fluorinating agents. So the compounds are not highly stable, so easily they provide fluorine. They act as fluorinating agent. So when the xenon fluorides combines with fluoride ion acceptors, they form cation. If xenon fluoride combines with fluorine donor like MF, sodium fluoride or potassium fluoride, they form anions. So here XeF6 is accepting fluorine, here XeF2 is donating fluorine, right? When xenon fluorides are combining with fluorine acceptors, they form cations. When xenon fluorides are combining with fluorine donors, they form anions. Next, anhydrides and their oxoacids. Anhydrides and oxoacids. So I am taking H2SO4. Remove all possible water molecules from H2SO4. You will get SO3. This SO3 is called anhydride. SO3 is an anhydride of sulfuric acid. SO3 is the anhydride of sulfuric acid, and H2SO4 is the hydrated form of SO3. These type of questions also important. Similarly, Cl2O is the anhydride of HCl. Cl2O7 is anhydride of HClO4, right? But see the ClO2. When ClO2 is dissolved in water, two oxoacids are formed. When ClO3 is dissolved in water, two oxoacids are formed. So that's why the ClO2 and ClO3 are called mixed anhydrides. Whenever the oxide is dissolved in water, if it produces two oxoacids, that is called mixed anhydride. So NO2 is also mixed anhydride. When NO2 is dissolved in water, it produces nitrous acid and nitric acid. So mixed anhydride, right? ClO2, ClO3, NO2, all these are mixed anhydrides. Now, here bleaching agents list I have given here. Bleaching agents list. Chlorine is a bleaching agent. Bleaching powder. This bleaching powder, CaOCl2, CaOCl and Cl. This chlorine is -1, this chlorine is +1. So, calcium hypochlorite is bleaching powder. Hydrogen peroxide bleaching agent. Chlorine dioxide is bleaching agent. And ozone is a bleaching agent. So, all these bleaching agent, chlorine, bleaching powder, this chlorine must be moist chlorine. Moist chlorine, bleaching powder, hydrogen peroxide, chlorine dioxide, ozone, all bleaches through oxidation process. The bleaching agents which bleaches through oxidation are permanent bleaching agents. All these are permanent bleaching agents. Sulfur dioxide, moist sulfur dioxide bleaches through reduction. These are all bleaching through oxidation. Bleaching agents through oxidation, permanent bleaching agents, bleaching through reduction, temporary bleaching agent. There is only one example here, sulfur dioxide, moist sulfur dioxide. It produces nascent hydrogen. That nascent hydrogen is responsible for bleaching the compound. So the process of removing natural color from organic substance is bleaching. So oxoacids, here different oxoacids are given. Basicity of all oxoacids is all oxoacids are sulfur 2, right? There is no difference. H2SO5. H2SO5 is peroxo acid, peroxomonosulfuric acid. It is also called Carros acid. And H2S2O8 peroxydisulfuric acid, it is called Marshall's acid. That is also one peroxo acid. Here, oxoacids of phosphorus is given. Generally, everyone is confused about H4P2O6. In H4P2O6, we have 4 POH, 2 phosphorus oxygen bonds, 1 PP bond. This is correct structure. So 1 PP bond is there and 4 OH bonds are there. 4 OH bonds and 2 oxygens are. P double bond O bonds are. This is the correct structure of H4P2O6. And these are the oxo acids of halogens. HOCl hypochlorous acid, HClO2 chlorous acid, HClO3 chloric acid, HClO4 perchloric acid. And remember, there is one oxo acid for fluorine, HOF, but that fluorine oxidation state is what? -1. This is from JD Lee. One of the standard reference book is JDL for inorganic chemistry. So in JDL it was mentioned that fluorine oxidation state in HOF is -1, not +1. So HOF, fluorine is -1, therefore oxygen is -2 and hydrogen is what? +1. So here you can see the structures of XO minus, I mean these oxoacid structures. Hypochlorite ion, chlorite ion, chlorite ion, perchlorate ion. These are the structures. Here important point is acidic nature of oxoacids of chlorine. HClO4 is greater than HClO3 is greater than HClO2, that is greater than HClO. This is acidic nature, fine. But oxidizing nature, ClO minus is greater than ClO2 minus, next ClO3 minus, next ClO4 minus. So generally what we will expect now, ClO4 minus should have higher oxidizing power. Generally the statement is the compounds with higher oxidation state act as strong oxidizing agent. For example, MnO4 minus, potassium permanganate, manganese +7, strong oxidizing agent, correct? Dichromate, chromium +6, strong oxidizing agent, right? So if the element is at its highest oxidation state, that's a strong oxidizing agent, but here we have an exception. In ClO4 minus, chlorine oxidation state is +7, that is the highest, but it is not the strong oxidizing agent. The reason is the ClO4 minus is stabilized by resonance. It is resonance stabilized. So this is structure ClO minus, double bond O, double bond O, double bond O. So it has extended resonance. This O minus is in conjugation with 3 double bonds. More extent of resonance is there. Due to resonance stabilization, the ClO4 minus not interested to undergo reduction, not interested to destruct itself. So ClO4 minus is stable. So among these, which is unstable, ClO minus is stable. It does not have resonance. That's why it is a strong oxidizing agent. Remember, in all other cases, the compound with higher oxidation state acts as strong oxidizing agent. But here exception is there. Due to resonance stabilization, ClO4 minus is weak oxidizing agent and ClO minus is a strong oxidizing agent. Next, these are the oxides of nitrogen. Nitrogen, NO, nitric oxide. This nitric oxide has one odd electron and NO2 is also odd electron. Due to presence of this odd electron, this NO2 is colored and NO is also colored, right? And NO forms dimer and NO2 also forms dimer. These structures are important. All these structures are important. They may ask how many single bonds, how many double bonds, or the number of lone pairs, or regarding odd electron species. These structures we need to practice. And the last topic is disproportionation reactions. Chlorine with cold and dilute sodium hydroxide, disproportionation. Chlorine with hot and concentrated sodium hydroxide, disproportionation. Hydrogen peroxide decomposition, disproportionation. Nitrous acid decomposition on heating, disproportionation. And when NO2 is dissolved in water, it is giving HNO2, HNO3, that is disproportionation. Next, fluorine does not disproportionate. See, for disproportionation, minimum 3 oxidation states are required, including 0. 0 is common for everyone, including 0. Minimum 3 oxidation states are required. Fluorine has only 2 oxidation states, -1 and 0. No other oxidation state. So fluorine does not disproportionate. And another point, this is one point, it should have minimum 3 oxidation state. But in those 3 oxidation state, the element should be at intermediate oxidation state. When the element is present at intermediate oxidation state, suppose the element is present at its lowest oxidation state, no disproportionation. If the element is present at its highest oxidation state, no disproportionation. When someone is present at intermediate oxidation state, it will go for oxidation as well as reduction, which causes disproportionation. So these are the conditions for disproportionation. They are phosphorus with sodium hydroxide and water on boiling, disproportionation. Sulfur with sodium hydroxide, disproportionation. S3PO3 on decomposition, S3PO2 on decomposition, and manganate, MnO2 minus, manganate in acidic medium, disproportionation, and Cu plus, disproportionation, Cu plus 2, Cu2 plus, and Cu. This is a disproportionation reaction. So these are the all possible disproportionation redox reaction related to our syllabus. As per the NCERT, as per the Neet syllabus, so these are the possible disproportionation redox reactions. I hope it is clear for everyone.